computer. Okay, so welcome again, everyone. And this recap session of summer semester, yes, of of 2023. I have a few things that I would like to mention before we begin. Okay, so this, as I said, this session will be very, very long. We will cover the entire material of this topic using these communal notes that we've all worked together and assembled throughout the years. And I find them very, very good. And I will go through the topics and I will focus on things that I find very important. And I will ask you relevant questions that I think that will guide you properly to the exam. Given the fact that all tutors contributed to the exam in some manner, I want you to focus you on how to do it properly. Okay, so a few notes. The exam is going to be, of course, most of you have already seen, but it's going to be between 16 to 30 pages of questions, and you only have 90 minutes. This means you're going to have 1 minute per point in this exam. This is very hard. Okay, for some of you, I guess for many of you, it's going to be the first exam at TUM. That was for me, and that was like a big of a shock. But it's definitely doable. Many people manage, many people succeed. But you just need a little bit of strategy. For that, I employed that you will save at least 1 exam for simulation. So you will not solve them all, like relaxedly. You want to have a complete simulation over the exam, so you don't face it for the first time in the exam, and that's it. Okay, so. And I want you to okay, so the first thing that you were going to have is going to be 1 multiple choice questions. It's usually very hard, and the way it is structured, it's if you you can have many different correct answers or not correct answers at all, but you'll have to score the exact amount of correct answers in each one of the questions. Otherwise, you lose all the points. It is not like partial. I don't know why it is like that, but it is how it's been and how it's structured. It's not up to us to make the rules about that. So be careful. Therefore, you should be very careful when choosing the questions. We try as the best we can to make it as clear as possible, so it's not vague. And if there is a vague question and a lot of people will make mistakes because of that, as we did last semester, we will of course change it and we'll give you the points. Okay, so for example, if I don't know if you've already looked, some exams have some back propagation questions. Well, you have to manually do back propagation question, calculate them by hand. These kind of questions take, they are worth a lot of points, but they take a lot of time. So what I would do when you face them in the exam, just skip them and come back to them, because the strategy that you wanted this exam is to get as many points as you can. Like I've never seen anyone managing to score the full points on this exam. Some people manage to do 87 out of 90, but it's like a single person out of 1,200 every semester. So I would like for the average of people, for the people that are in the middle of the Gaussian, just try to skip the hard ones and go fix on the theoretical one first, because calculation, especially when you're stressed out, could take a lot of time. I don't know if you've created, maybe it's too late for that right now. It's never too late. Never say never. Create a study group. It was 87. Create a study group. For me, that was the best way to learn, because first of all, if I had any question, I could immediately have some response or discussion, and I could teach what I think I know, or maybe get some critic for what I know. And therefore, I managed to score the exam. I'm very terrible in exams. That's what I've learned in university. And with that, I managed actually to score a pretty nice score here and to become a tutor at this course and to get to all these new advanced learning, deep learning courses at TUM that I wanted. So keep that in mind. Maybe it doesn't work for you, but for me it did. Okay, don't skip the hard topics. So the lecture 12 discussed a lot of new advanced topics. And don't skip this one. For me, that was super easy to say, oh, but what is the odds that they're gonna ask us about it? We are gonna ask just a few questions, and usually we focus on variational autoencoders and with high level details. For example, what is the main difference in architecture then from autoencoder? Or for example, during training, so for example, using different loss function and the latent space, how it is structured. Or for example, during inference, how do we use a variational autoencoder? We don't, for example, here, we don't use the decoder anymore. That's what you need to know. You don't need to know more than that. Or GANs. For some reason, people like to ask about GANs, although it's a very advanced topic. So here you need to know that they have a single main function loss, and then you use it. How we use this for the discriminator and the generator. What's the difference between this and autoencoder or variational autoencoder when it comes to the latent space? And I think, but for example, all the discussion about diffusion, stable diffusion, stuff like that, we're not going to ask you. This is very hard topic, very mathematical, and we did not dive into it. It's just good to know and to show you what this world has to offer when you move on from this course. Okay. Quickly. Okay. Now, the thing is that for you, when you come to write questions in the exam, for example, what I want you to prepare right now before we start, I'm going to ask you questions throughout this recap session and things that I find relevant. So I want you to have a pen and paper and try I'm going to ask you and give you some time to answer. And I want you to try to solve them with a pen and paper, because it's a good practice. And many of us don't write anymore with a pen, and it's a skill that we all forget. It has your answers have to be precise and they have to be short. And why is that? Because first of all, for us, it's hard to read your stories. Many of us have bad handwriting, especially after not training it. And it's hard for us to read what you're trying to do. And then we're looking for keywords. And if you have a big story, you might have something that are correct, something that are not correct. And then you will not have full points, because a full scoring answer would be something precise that has only what we desired, because this is a competitive exam, and some people should have better results than others. So it has to be precise, and it has to be, and you have to think, if you answer exactly what we asked you, and not start to give us information from any other topic that might, as you're not sure about, but you think to yourself, oh, maybe I'll put it down and it will grant me some points. Usually it doesn't. Okay, and so you'll just waste time, very precious time that you could use otherwise. I saw one of the old exams shared with us the question about specific CNN filters, weights are given, and what they do. Also, there are questions about the size of different images recognition models. It's a bit tough to remember stuff like that. Should we expect question like that in the exam? I need to see what you're talking about. This is quite out of context for me right now. If you do it on Piazza, I will of course be able to give you a better answer. I want to discuss how to write questions on Piazza, but before that, okay, so for example, computer vision, topics that usually people don't study or don't focus on when studying for this exam. For example, computer vision. What I mean by computer vision, this deep learning course is a part of computer vision, and we deal, for example, with convolutions that are computer vision related or focused. So I want you to understand what is a tensor and how in computer vision we look at a tensor. For example, what is an RGB image, and what are the values of what is the range of values that are inside? For example, that in an image we always expect the values to be positive and between 0 and 1, or 0 to 255, or that you have 8-bit. That's something we want to ask about 8 bits, because that's advanced computer science stuff. But what do we expect to see? Okay, so for example, we could ask you stuff. If I want to visualize something, what I need, what I need my tensors to hold. Can I have a normalized image and then to visualize it? No, because then we'll have negative values that computer library or Python libraries that want to visualize an image just don't know how to handle. Okay, stuff like that. It's important because this is part of computer vision. This is part of being a deep learning architecture in this field. Requires you to know this kind of stuff. And we don't only train you to solve this exam. We want you to be able to go out into the world and deal with real world projects. Data loading, exercise 3. People, I guess, will just scan through this, but I find it super crucial from my experience. What is the difference between data loader and data sets, for example? What are the important functionalities that we have there? What kind of transformation can we do? Some transformation are applied only to the training split, and some transformations are applied to all the splits. Or, for example, this is super crucial to understand. For example, data augmentation we'll do only for the training split. And then I could ask you in the exam, okay, what kind of splits do we apply that transformation to and why? Okay. And for example, normalization has to be applied to all of the splits. And why? Why is that? So I could answer it for you right now, or we could do it as an exercise and you will do it for yourself. Since it's not in this lecture notes, maybe we could solve it right now together, off the batch. Okay, for example, why data augmentation? Why do I apply it only to the training set and not to the validation and test set? Now, the way I want you to answer it is either you open your mic and you participate, or you write it in the chat that we have here. And later on, I will show you how I want you to write relevant questions on Piazza. So let's take half a minute together, and someone please write something in the chat. And let's have a quick discussion about it. Data augmentation, why is it only on the training set or training split and not on the testing/validation?
Can you hear me?
Oh. Yes.
Okay, I think someone else answered already, but data augmentation is only applied on the training set because we want to kind of widen the input that we have for our training. So, or not like just widen, also like ensure generalization and complexity of our input. And therefore we use data augmentation, whereas with validation and testing, it's more about like trying to see how great our model works after that kind of more generalized input that we give through data augmentation.
That's a good answer. You just forgot to mention that the training /validation is the representation of the real world data. We don't need, basically, like we assume when we come to the data set that the training set, this is the world, nothing else exists in this world. This is what the world has. So we don't need to change it. Okay, for exactly, you said generalization, which is great. And we want to see generalization on this real world data that we have. Okay. And that was just a little thing missing, but of course, I think that your answer will get full points on the exam. Let's see what other people said. This is a regularization technique, so we wanted to enhance generalization. This is just measuring the. Okay, again, Benjamin, exact same point. Validation should contain real data. Exactly, to explain training option, make a robust validation. We don't need this performed algorithm. Okay, so most of you say the exact same thing. Very good to say this is a realization algorithm that checks the generalization because the test and validation represent the real world data. Okay, that's what I think I'm missing from all of your answers. Okay, because you don't tackle the point. Okay, but what if I did? What does it matter? Okay, but because I could, for example, flip all the validations images, right? But then it will make the validation set even bigger, which will make our testing of a generalization quite hard, because we don't know, because we just need the validation set to see if we generalize to this. We can't tell from that if we did good, we did bad. Okay. Yes, exactly. It's going to be hard to compare the performance between models. Also a very good answer. Okay, perfect. So this is how it's going to be during this recap. Okay, I'm going to ask you this question. We're going to have a discussion, and I'm going to point out things that I find good, point that I find out right. And very good, guys, for trying to make it as precise as possible. Also, before we continue, I want you to be able to ask questions. Now, it will be hard because I'm only one person here, and you are 125 people. And I want you to be able to write questions. So what I want you to do, go to Piazza. I'm not going to do it now because I'm sharing my tablet, but I want you to go to Piazza and see the recap example of how I wrote a question on Piazza. There is a folder called recap, like we have exam or exercise 1, whatever the Piazza requires. So it's going to be recap, and I want you to open the title with recap, the 2 dots, and then your question, and then you could, of course, start a discussion, and you could be able to read it and answer. And later on, if someone wants to see only the recap stuff, they could just write recap in the search bar, and they will have all the questions from the recap. And that's what the best way to search for it. Okay, that's what I want you to, how I want you to ask questions. Of course, you can also ask relevant, specific, that I'm talking of things that we're discussing right now in the chat, and I will try to answer. Okay. But if you have, so for example, things that you don't want to forget, or you want some general stuff, Piazza, please. And of course, I want you to be able to, I want you to help others. So I want you to try to answer questions yourself. If someone posts a question on Piazza, I want you to try and answer, because that's the best way to learn. Okay, try to be a part of the discussion. In Piazza, you can be anonymous, so it doesn't matter. People won't know that you made a mistake or whatever. Okay, so please try. Okay, so let's begin. Okay, so just remember, don't skip exercise 3 and the relevant stuff that we discussed there. For example, normalization, data augmentation, how to load data, super important. Okay, so let's begin. From the very beginning, we have, as always, some some machine learning topics, I think. Yeah. Okay, so the differences between linear regression and logistic regression. Okay, it's a very easy, simple question. To which kind of problems do we apply linear regression? Linear problems. Logistic regression, and the difference between logistic regression, yes, and linear regression. What is the difference? If I ask you that in the exam, what could you answer? It's one sentence in the chat. There's something that we ask. So, okay, Benjamin, you're almost there. Linear regression and the logistic. Okay. Okay, I think who answered? I think that was Abdelrahman. I think that's your name. Perfect. Linear regression is for regression problems, and logistic regression is for classification problems. Okay, so we have different tasks in what we did in this exercise. In this course, for example, we did image reconstruction in autoencoder, which was a regression problem, because each pixel, we tried to compare it to the original pixel in regression-wise, in the between the output and the input. And semantic segmentation or image classification is to put stuff into bins, which is a non-linear problem, as many people of you just said. And that's the biggest difference. There was an exam questions that people asked on Piazza. If logistic regression is linear problem, not linear, it's of course non-linear because we use the sigmoid. It is a regression though, okay, because because using just the linear like the linear function, a fine layer, then sigmoid is still a regression problem because it sends you to a continuous value on the sigmoid curve, and then we use a threshold to classify stuff. And this is a simple detail that is important to know. Okay. Okay, let's continue. I'm not going to focus on a matrix notation. This is something, yes, this is something I like, and I made a question about in previous exam, that linear regression has a closed form solution. Okay, this is something that is actually quite useful. And usually you will not want, I asked in previous exam, why don't you want to solve linear problems with, or linear regression problems with deep learning? Because of that. Because you have a closed form solution, given the fact that you could put it all in the RAM. Okay, that's also something that is important to know. It's like with the Gauss-Newton algorithms optimizers. If you can put everything in the RAM, on the RAM, amazing, let's use something that we can use. For example, you could use deep learning to solve this kind of stuff if you use some linear regression with images or whatever, that are a very non-convex problem. So for example, that, okay, so you cannot put all your images in the RAM, and therefore, like for example, I think Cypher 10 we could, right? Doing the exercise we could actually, and that you could solve with linear, with this closed form solution. We do not expect you to know this closed form solution, okay? This is not machine learning course, but but in context of deep learning, that's a good question. Okay, why? To which problems do we want to apply deep learning in the first place? Deep learning takes so much resources and time. Sometimes there are better solutions. Okay. What is closed form solution exactly? The closed form solution exactly is a solution that solves the problem in single, like it's like solving a linear system, as you could see in this system here. Basically, you just plug in your inputs, the x's, and all the inputs that you have, and you solve it, and you get a solution. You could do it on paper, for example, and just get a solution. Okay. Okay. Let's see if I missed any question. No, people gave solutions. Very, very good. The things that I want to focus on. Okay. So I'm not going to focus on this part, yes, on how to derive this kind of stuff, this closed solution. This is just for you, for global knowledge. What I do want you to tell me, it's why do we derive eventually the formula, I think, that is here, right? The using of the logarithm. Why do we use the log? So that's a question that could be asked. It's not that likely to be asked because it's quite irrelevant. But why do we use the log in for example, the cross entropy loss that is derived from the Gaussian? Why we don't just use the Gaussian probability, this thing? Okay, has a continuous smooth slope. Okay. Amazing. Okay, so Jacob said it right. To convert the product, this thing that is super hard to compute into a sum, and compute also by paper, also for the derivative, to compute it into a sum. But the one that was said by Rog has a continuous and smooth slope. It maintains the ratio, so between numbers. So, for example, two numbers that one number is bigger than the other will remain in the same ratio, which is super important for our task. Yes, retains monotonicity. Shusti, thank you very much. That's the exact term. Perfect. Yes, Gao, very good. Okay. I will not go over this, the revision. This one student last semester did it for you guys to be able to follow, if you want, how it was derived. But the thing is that I think we'll discuss it here. I think the differences between, just to see, you remember that it always goes back to the differences between, oh, here, this one, this one, this one, and this one. Okay, perfect. So as we just discussed, we have two different tasks in deep learning, right? We have, and each task would have a corresponding loss function. And this is something we really like to ask. So for example, I give you a task, okay? I give you a task that you need to tell me what's in the image. That's like a super relaxed problem, right? Like we discussed it the entire course. You need to tell me what's in the image. Is it a dog? Is it a cat? What kind of a task is it? It is a classification problem. What loss functions do I need to deploy here? It depends, of course, on how many classes we have. But if, for example, we have two, so it could have either the binary cross entropy or it could have the cross entropy. And we're doing currently the unsupervised autoencoder. Okay, and I want to reconstruct the image. Okay, I want to denoise the image. I want to do super resolution image. Okay, what problem is that? This is a regression problem. What loss function comes along? Either it could be any variance of the L1 or L2, but this is what we need you to know right now. Okay, so, and of course the MSE and the MAE are just the synonyms, and I'm not saying it right, but it is just the different naming for this kind of these numbers. The L2 or L1 losses both are acceptable. Okay, but just for you, if we say in the exam MSE or MAE, that you know what we're talking about. Okay. Okay, the question that came on Piazza, and I like, what is the difference between the cross entropy loss for two classes and the binary cross entropy for the binary cross entropy? Can you tell me the difference in architecture-wise? Regression-wise will be always pixel. It depends on the task, yeah, but for construction will be pixel-wise because you want to reconstruct it for every pixel. Perfect. Okay, Benjamin answered correctly. So the BCE would have one output, and the CE would have two. Okay, and definitely, so basically, it's the same function. It does the same thing if you just look at it. The thing is that they do use different activation functions. And remember, this is something also that I already say. Remember that we separate the let's go here, for example. Let's say this is a, no, I don't. I need a null network, null network. Is there a null network here? Why so many things? Okay, went too far, definitely went too far. Is there a null network here that I could discuss? Let's see here. Okay, a null network, okay? We separate this part from the loss function that comes here. Two different things, okay? We talk about them differently. The loss function comes with relevant loss functions, comes with different activation functions. Regressions usually don't come with any. You could do it if you think it's relevant. For example, where we did it in exercise 9, I think, with the key points, and people use tan H on the logits because they wanted to squeeze them between -1 and 1. Definitely okay. But we're definitely okay. You could use it as the different part of the architecture. But cross entropy and binary cross entropy come with default activation functions that are not relevant in the network. So, for example, this is a network that does binary cross entropy because we have, for example, it could be a regression, yeah, but it could also be binary cross entropy because it has one single neuron at the end, and then we apply what comes with BCE. A ROG, yes. Sigmoid, perfect. What come with CE? The softmax. And I'm saying that basically both of them could be used and there will be the same. Not really, because softmax is different than sigmoid. Just works differently. Okay, perfect. And this question comes back in every exam. Okay, super easy in the, for example, the multiple choice. Yeah, people just lose points on that for no reason. this CE comes with softmax, BCE comes with sigmoid, nothing else. Okay, and the L1 and L2 don't come with default one. You could attach something, you don't have to. Okay, perfect. What else? There was a question, so we would, yes, the one-hot encoding. And guys, if the term one-hot encoding doesn't tell you anything, stop me and I will explain. But before that, let's see if I have something that I want to discuss before we move on. This is the loss function and the optimizer step, but that will be an optimization, backpropagation and optimization, computational graph. And this we have some activation functions. Okay, so let's discuss first some things of neural networks that I always find confusing. Okay, there were just were exam questions that asked you to do backpropagation on neural networks, and the indexing was super confusing for people that just didn't know what we mean. The sigmoid is just a function that pushes between 0 and 1 in some manner, and the softmax does it in different manner. And softmax pushes stuff that are bigger into be bigger and slower stuff to be smaller. So the differences between the probabilities, because why do we use them? That's also an exam question. Why do we use these activation functions? Because we want to have probability-like functions, num values to be used later on as probabilities in the loss functions that we want to either push to 0 or to 1. Okay, so yes, so let's do one-hot encoding. Okay, so let's say we have two here. So let's say we have two classes, and we have I will explain later on how we look at the neural network. Okay, so we have two different logits. Okay, the values that the network outputs, and the one-hot encoding is basically saying for each one of the images in the batch, it's going to be a vector of the same length of the logits, yes, that has zeros everywhere where okay, it's going to be 1 only where the real ground truth is, and 0 otherwise. That's what I wanted to say. So let's say we have 0 and 1, and let's say that we have horse, and horse is 1. Okay. So it's going, and so the one-hot encoding is going to be a vector of 0 and 1. Okay, that is corresponds to the logits. And why is it important? You don't really have to use it because when you implement it in architecture, but the loss functions, if you recall, is a sum, right? This is the cross entropy loss, and it sums over all the k's. The k's is the length of the number of classes. It could, if it's confusing, you could do C, okay? And basically it sums all of them. So it does Yij, this is the index in the one-hot encoding. So let's say we have 10 of them. So we're going to 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, so it's going to be 0, okay, 0, 0, and then it's going to be just 1. So only the 1 is taken here into consideration. That's just the point of it. For this, it's just meant for this sum. When you implement it, you could just take where it's you could just take the logits with the corresponding ground truth, and that's it. Okay, you don't need to implement the one-hot encoding. Okay, if there are any questions about that, can you say the segments of not used for generalization to evaluate probability distribution? Probability-like, it's not really a probability, right? But it's like, it's not the real probability of something. We try to estimate this probability, basically, okay? If you write, but if you don't write the probability like in the exam, you will not lose points for that. Okay, it's just fine details that I like. Okay, the thing that I want to discuss right now is to go back here and to discuss how do we look of a sketch of a neural network. Okay, a sketch of a neural network. We always look on this sketch as we have a single image or single input in the batch. It doesn't matter if we have 16 images in the batch, 32, 128. When we look at this sketch, it's only looking at one. When I came to do deep learning for the first time, I didn't understand what am I looking at. Like they said, we pushed 32 images into the network at one time, and I thought, oh, is this an image? This is what represent? No, it introduces. This introduces a single input, and this one is an entry in this tensor of the input. Okay, or what we call a neuron, and this is something that still comes up on Piazza. What is a neuron? So what do we have in our architectures? We have input values, and we have weights. That's all we have. It's either some value that we use as input to some layer, or we have weights. So inputs we call neurons, weights we call weights. Okay, this is just the difference. This is how the brain works. This is what it tries to mimic. Okay, so the neurons are those values, the inputs that we try to do. This is the input to the first layer. This is the input to the second layer. So this is also a neuron. The weights are those edges. Okay, and these are called weights. So don't confuse the weights with neurons. So for how many neurons do we have in the input? We have 3. How many neurons do we have in this hidden layer? We have 4. How many neurons do we have at the output here? We have a single neuron. That's what just the terminology, but people still find it confusing. Okay, how do we do it with indices? So for example, we have a layer. Okay, we want to do the weight. I want to have this weight. Okay, this weight that goes from the 0 entry of the input to the 0 output, the entry in the output, and in the first layer, on 0 layer, okay? So we will have the weight at L, input, out, okay? Always like that. This is just the easiest way to remember. So this weight is gonna be W0, 0. This one is gonna be layer 1, right? This is 0, this is 1. 0, 1, 2, 3. 1, 2. That's it. Weight 1, 3, 2. Okay? Any questions about that? The only question that we had was, I think, summer semester 21. Which layer is the weight? You mean, like, I mean, so this is the layer, yeah? Like this is input, this is input, this is weights, and layers are relevant to, like, layer represents some affine layer of convolutions which have weights. No, this is layer. This is layer. This is not layer. This is okay. This is just output between. These the weights are the layers. When we do hidden layer or we do activation, when we do a fully connected layer, it's where we apply the weights, the layer between these. Okay. So this is the first layer, 0. Why 2? This one is this. If this is 1, if this is 0, this is 1, right? This is 2. Yes, and if I did, yeah, that's true. 1, 3, 2. If I didn't do it right, so that was my mistake. I don't have it written anymore. Okay, so this is the simple thing about the sketches of neural network. A question about terminology. Layer has weights and biases. An apparatus of layer is weights and biases, but because biases are also weights. We just call them differently because it's not like the weight matrix. Okay, but it's important because they also have derivatives or number of, when we say number, they are all parameters. Okay, that's the network has, that it takes into consideration. So this is yes. So the bias is just a separate thing, a separate variable that we add, but there's also a learnable parameter, which is important because people forget that. Later on, when we do convolutions and we will ask you how many parameters in this convolution layer, you need to, and if we say consider the biases also, you need to know to consider that because it's learnable. Okay, anything else that I wanted to do about that? Let's see. Yes, okay, so basically when we will come to the backpropagation, I will not discuss it here. So if in the example we ask parameter for the first layer here, it will be 16. 3 to 4 and 4. Yes, exactly, yes. Jakob. Okay, the backpropagation, the Stanford article that we dealt a lot during the beginning of the semester. All you need to know is the tricks. I will not expect you to derive it by yourself in the exam. Definitely not, because it's not an official thing. Because they didn't put it in the lecture, right? It's something I gave to you. But it is possible to ask you the final result, because derivatives, it's something you need to know how to do. That's what the exercises. You need to know how to derive inside neural networks to find the derivative of some tensor. And that's something you need to know. So you just need to know the bottom line of how to define the derivatives of stuff in a fully connected layer, not in convolutions. We did not teach you how to do convolutions, although it is done exactly like fully connected layers, but we did not touch it. We're not going to ask you how it's done. Okay, so for fully connected layers, it was a question in the exam that I wrote 2 semesters ago, and you had to just calculate it by hand. Those who just reviewed the article before the exam knew how to solve it. It was super easy to do, at least I find it like that. Because if you just know just to do a bit of matrix multiplications, just 2 on 2 with something, and nothing too complex. Okay. So that's something you should know, but I'm not gonna discuss it here. If you want later on, we could discuss it on Piazza. Okay, activation functions. Let's see if this is what I want to discuss right now, because then we go to backpropagation, regularization already, and then optimization. This is SGT. Okay, so let's discuss activation functions. Okay, if you're following me, I am in page 13. We've seen many activation functions in this course. The questions that we like to ask about this kind of stuff is, what is the most common one? What problems do sigmoid and tanh has in comparison to ReLU, and why? And I want to have this discussion right now. So the sigmoid and tanh was in the very early steps before ReLU was introduced. And they had a major problem when we wanted to dive into deep neural networks. What is the problem? And this is something in an ongoing discussion on Piazza. How do we call the problems the tanh? Okay, so this is a quick exam question. Name 2 problems that they have. The vanishing gradient, that's the keyword that I'm looking for. Thank you. Saturated neurons causes the vanishing gradient. Okay, this is the cause. Non-zero centered, very good. Sigmoid is not. What is, by the way, if I ask you that in the exam, what is not zero centered? No. What is not? Not an example. What is it? Okay, Ekaterina, that's the exact answer. The output is only non-negative. It could be 0, right? Like ReLU is non-zero centered, but it doesn't have to be that the mean is 0. It just doesn't have any. One of the sides of the 0 does not exist. So it could be like minus ReLU is also non-zero, but it also has negative, right? Yes, so leaky ReLU is zero-centered. Yes, the mean doesn't have to be, but also I wouldn't say the median is 0. Like I definitely wouldn't go there. It could definitely not be the case that the mean is shifted unless we normalize. So I wouldn't go there. And again, it doesn't have to be symmetrical, right? No, leaky ReLU is considered zero-centered, and it's definitely not symmetrical. So for example, this is a great example of what I expect you not to do in the exam. Don't go this way. Don't try to invent the wheel. So ReLU is not zero-centered. That's true because of the definition that we just said here, that the output is only non-negative or non-positive, one of the others of the two. Oh, why can we do it? Because it saturates at the zero. It breaks this continuity. It's basically non-linear function. If you try to like the easiest way to say is just to say ReLU is non-linear function, a linear function, and you try to deploy it like with what is a linear function? It's when it's linear. When f of x of y equals f of x plus f of y, and with multiplication also, right? Or with a scalar. So f of a of x equals a multiply f of x, and that just doesn't answer the question. And so why a non-zero-centered sigmoid a problem? It's not that big of a problem, okay? But it causes it has a problem where it makes gradients to be of sometimes, not always, sometimes to be of the same value, and then makes it quite harder to get, because what we need to know is to cause the zigzag effect on the way to the minima. For example, let me just draw it. So basically we have a minima here and we have here, and there's at some cases, not always, like for example, if the only activation function in the network is sigmoid, it could happen that it will go like this. Also with ReLU, it could happen, but it's not that big of a problem. Okay, it's not as big of a problem like the vanishing gradient. Okay, it's just a problem that exists there, and you don't need to know more than that. Then if you say non-zero centered, you say zigzag problem, you got the point. So go, that's the thing. When it came on Piazza this semester, I went again and tried to deal with it. And it's such an open question because in many cases, it's not the case. So it could cause this, like basically you would always have to just say, I will ask you what mention a disadvantage of sigmoid that you would say non-zero center that you'll get the points. Okay, like it's much more complicated than just to say it's always have the same sign. It's at least what from my experiments. Yes, and that's Matteo. That's the next point I want to get to. Okay, so I will not ask you this. I'm going to explain now what's the difference between the vanishing gradient and the dead ReLU. Okay, and that's something that went on Piazza. And we decided as the course like tutors or maintainers that it's not that the reason it's a crucial difference because some of this the vanishing gradient could be solved in some manners and the dead ReLU could be solved in other manners. Okay, they're not the same problem. And what is the vanishing gradient? The vanishing gradient is that we have a deep network, okay, that has, let's say, sigmoids in the middle. Okay, between each layer has a sigmoid, like a fully connected layer and a sigmoid. What's the problem with sigmoid? It has two main problems. As many of you just said, it saturates for bigger number or for example, numbers with bigger magnitude in absolute value. Why? Okay, just before I continue, why is it? I'll just answer it later because I don't want to mix it up. Okay, so the sigmoid saturates, or it has a very small gradient, like its highest derivative value is 0.25. So it's in contrast to ReLU, which maintains the magnitude of the value if it's positive. Okay, so first of all, it makes the gradients already very small, even with the highest one. But when we go to the edges, it's become super small, the gradient, yes? And then it means the gradient when it propagates through the network, it becomes smaller and smaller and smaller. What is the problem? It means these the deeper layers could still train because their magnitude of gradient would still be reasonable. But when we go up and up and up the stream, the gradient will be so small, it will be, these layers will basically or train much, much slower or not at all. This is the vanishing gradient problem, which could be solved also by the Xavier initialization that keeps the variance of the layers the same, or easier with skip connections. Yes, if we have this is some weight function, and this is a skip connection. The gradient then propagates on this, and its magnitude doesn't diminish. And this is a great solution, the best solution. Also, initialization is important, but the best solution for this would be to use skip connections, which are a very good advantage of skip connections is that they are very, very low in computations. They don't require much at all. And of course, that they solve the gradient, the vanishing gradient problem. Okay, let me just answer some questions. They don't solve the exploding gradient problem. Okay, that's something else. But the vanishing gradient they solve. Okay, why is non-zero-centered sigmoid a problem? It's not because it could enforce with the E. Think that the network should just go in a bit more of a zigzag. It introduces more noise to the network and to the training. It will take for the network longer to train. In rel or liquid rel, what do we have to do? Apply if a derivative to 0? If we have, this is what we do in programming. We just say, okay, derivative of 0 would be 0. Okay, we specifically say it. It is always positive gradient for associated weights should always, okay, is there a difference between vanishing gradient? We'll just discuss it. This is the vanishing gradient. Why sigmoid is being seriously to Brad? I think I just answered because the gradient, okay, thank you for Katerina to answer. Tan H is zero-centered, but it also saturates. That's true. That's true that it doesn't suffer from this problem. It just saturates. Okay, like and the biggest gradient of by the way, a question that could happen in the exam is to represent tan H with sigmoid, which you should know. Think it's 2 sigmoid x or 2x minus 1. Okay, you should know that. Also the derivative of it, which is 1 minus tan H to the power of 2. Okay, and you should know how to derive it. Our skip connections for connected networks, I think they only talked. That's true, but you could do it for Jacob. You asked for full skip connections for fully connected layers and convolutions. There, of course, you could do it also with fully connected layers. I will come to discuss the difference between fully connected and convolutions later on, but of course you could do it. The thing is, you always just need to make sure that they have the same size, right? Like that's the most important thing. What you want to do, actually do addition, or if you do concatenation, it doesn't matter. But if you do addition, the tensors have to have the same size. And a question that could happen is not just theoretical. Deep learning is a practical mathematical thing, and you need to know that you need to have the same sizes of the tensors. What about exploding gradients? That not to keep problem activation functions? It depends which one. It's more architectural problem. For example, when it comes to RNNs, if the how do you call it? The eigenvalues are bigger than 0, than 1, then you will multiply with values that are bigger than 1, then it will go bigger, 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 because we use the same weights again and again and again, and then it will explode. That's an exploding that could happen. Also, if you don't normalize the inputs or throughout the network, normalizing solves the problem of explosion completely. If you don't normalize, and you could have bigger numbers that would just explode and out of control. Not necessarily because of the activation functions. Saturating and exploding gradients, there is no much of difference. They're just two different things. Saturating. What is saturation? Is to have the from the left and from the right, basically very, very similar numbers. And saturation also, that's just what we mean by saturation. Exploding is when the gradients basically become, for each iteration, bigger and bigger and bigger until it's out of control. The network doesn't know what to do with them. Après, for skip connections, so it's just it's a matter of cost. If you do concatenation, you'll have to have more parameters in the next layer. If you do addition, you don't need to, but concatenation will have more information. And what is the remaining answer for difference between vanishing gradient and dead ReLU? Okay. So dead ReLU, the dead ReLU means that if without proper initialization, when I use a ReLU, it basically kills, let's just take one. So remember that the derivative of W, yes, the dW is X transpose D out. Okay. And if this is the input that comes from the previous layer, and after ReLU, some of these, usually half of it, if it was normalized before, would be 0. Okay, it means that the derivative of W, a lot of it will be 0. The derivative will be 0. Okay, that's killing this. It doesn't happen every iteration for each entry. It could for some extreme cases, but the derivative doesn't even exist here. That's dying ReLU. Okay, for some bad initialization of ReLU, that could definitely happen. That's for all iterations. They will just definitely won't learn. Parameters will just get stuck and won't learn. In contrast to vanishing gradient, what they do learn, and depends on which layer. In the shallow layer, they could not learn because the magnitude is small, very, very small, almost 0. Yes, but here that's happened no matter where. That just happens. It just doesn't let it learn. And that's the problem with ReLU. So regarding the tensor, we cannot have skip connection between a layer with outputs. You can have a skip connection layer if you do concatenation for any different sizes. If you do addition, you have to have the same. And that's a question I like to ask in exams. Okay, what Jakob asked. Utku, dead ReLU is about variance of weights. I think dead ReLU kills. Yes, that's true. That's true. And a good solution for that. And I just wanted to do it intuitive, not to go into the mathematical part. But the solution for that would be to use the k-mean initialization, not the Xavier, the k-mean or the HE one. There's two names for the same thing. And that's a question also that comes back in every exam. Okay, what's the difference between the Xavier and the k-mean initialization? To which activation functions do they belong, and why do we use? Okay, because the Xavier initialization that solves the vanishing gradient doesn't do it for the ReLU. It's not the same. It's like not the same variance at each level. It's just different problems. Okay, and it's good to know, because when you come to your network as a deep learning engineer and you have problems and you need to understand, it's good to know the differences, because you need to understand what you should debug, what you should look for. I could not understand the question and the answer completely regarding Jacob's question about skip connection. Could you repeat it, please? So Jacob asked if I have this, okay, and I want to do skip connection between these two. Okay, this is a fully connected layer, and I want to take this input and squeeze it here. Of course, you can't if you do addition between the output and the input, right? You can't, because they don't have the same number of neurons. If you do concatenation, then this will have 1, 2, 3. This is the input, and then 1, 2, 3, 4, and this will be the new input, and this will go, for example, to 3 if we don't have any other skip connections. Okay, this will just. So this you could do if you do concatenation. You don't have to keep the sizes. But if you do addition, you have to do it. Okay. Okay, Bertie. Perfect. Okay, parametric ReLU. It's a thing you should know. it was asked once, and I think it's just not fair question because we never used it. It's not used in anywhere in practice. Bye bye. Max out also never asked in practice. Never used in practice. It was offered as an option. And what is the problem with max out? Is that it's a great idea. It just requires to have two weight functions in one layer, basically making, if the network using fully connected layer is already super heavy in parameters, and then you double it. Okay, that's just for real world applications, very bad idea. Therefore, never used. Okay, and ELU is just another nice one. I'm not going to ask you about it, so I'm not going to get stuck on it. Okay, anything? Okay, so any other questions of activation functions that we did not deal with? Let's see if I have anything in mind. It's something that is important. We did activation functions of loss functions. ELU, I'm not sure, actually. I don't think so. I think this is the constant. The wait, oh, it was deleted. Okay, so the best choice is the leaky ReLU. Not necessarily, because leaky ReLU requires more computations, and ReLU showed just great enough options. Because even though with good initialization, ReLU works just fine. There are better ones these days today, like Silo and Gelu and many other things. ReLU is actually not used anymore, but I wouldn't say what's the best one. So to be vanishing fixed by skip connection, exploding fixed by normalization, yes. Two. Okay, should we continue? What time is it? Yes, we have some time. 1 more hour, okay, until we have a break. So I think this is time to what do I want to discuss here? Here I just want to point out that this is a scalar. Remember, always the L is always a scalar. This is why the gradient is always has to have the same shape, okay, because this is a scalar. The normalization by n is super important, because why do we normalize the loss function by n? What is n? First of all, what is n, and why do we normalize by it?
The number of samples in the mini batch.
Okay, not just. It's true, like it's a specific case when we do image classification, but when we do semantic segmentation or image reconstruction, what is the n? When we have each pixel-wise comparison.
Total number of pixels?
It's the number of residuals that we calculate for the loss function. All the residuals, okay? For image classification, each image will have one residual, right? That it's GT with its corresponding logit or after activation, right? But for semantic segmentation and image reconstructor, for autoencoder, for example, we have, for each image, we could have the image size, as people said here, the spatial size of residuals, like H multiplied by W, and then we have it across the batch. So it's batch multiplied by the number of residuals. Basically, the number of residuals that we calculate for the loss, that's n. And why is it important? Like that's the Nikita said, area of image. Why is it important? Why do we normalize? No one said yet. Yeah, but we could have the average, like the average is taken into consideration when you have them all in one sum. Yes, Nicolas is right. The gradients would simply be too big. We want to have the magnitude as if it was a single residual. This takes the average, of course, of all of them and gives us like average direction. But the explode, if you don't do it, your as Gao said, residual is basically this. This one, your input, a residual is the difference between two numbers and the ground truth. This is a residual. Sorry if I should have said.
Sorry, so if an output consists of two numbers, then we have to divide by 2. But also if we have multiple samples in the mini batch, then we have to divide by 2 times the samples in the mini batch.
It depends if you have, for example, image classification and you have 3 different the number of residuals is basically only the one that takes into consideration here. Like you said, you remember that we did the one hot encoding that we took the zeros for all the, if this is the right ground truth, this is the right label, and these are not really considered. We don't take your multiply by 3 because we don't need them. This was just the formula. We just take this one and we take this in consideration. Only the ones that you calculate that contribute to the loss are taken into the consideration here. Yes, and Jakob, could we not just use small learning rate? So Marcus, I will not go down this way because once you make 2 variables dependent on each other, it will never end, okay? Because you've changed something here and then you say, oh my God, I have to also to change this. Instead of just, when you change the number of pixels in the image, or you change sizes or whatever, and then you just deal with it in the loss function. I will not go down this way. This is not a good practice to just use a smaller learning rate. It could solve it. It's not a good solution though.
So if there was an exam question to describe what n is, what would be the sentence to say? It's just the number of residuals, that's correct? Or the number of residuals times the...
Yes, you will never be asked that, but I started teaching that because we had some previous exams with questions that had, we didn't give it to you this semester, but some people found it, I think for 2019, you had eventually, the network ended with this kind of feature map, which had 4 different values. And then you had to do a loss function. And people didn't understand, but we didn't have 2 images. So why do we divide by 4? Or why do we do stuff? Because if we take some residuals into consideration, we have to divide by it. It was a bad question, definitely a bad question, but it's just to sharpen these rules. Yunpeng, how to spell Vitsu? I'm not sure that I understand. Maybe I just pronounce it wrong. Okay, I think we could continue. Unless I find something here that is important. Let's see if I have something in my own notes. A deep learning pipeline, regression, loss functions. I actually have some questions for you. Difference between L1 and L2, KN, PSCA. Okay, exam question that came back, because before I continue and I move on to the optimization and optimizers, I want to discuss, I have some questions that I've prepared for you last semester. Let's ask them, shall we? Okay, so for example, name all the steps of deep learning pipeline. So that's just, but usually it comes with a question. I'm not going to do it here. You need to just to have it and then to put them in place. Just basically loading the data, maybe applying data augmentation, then doing forward pass, backward pass, and optimizer step, etc., etc., etc. Okay, how do I read neural network? By indices? I showed you how to read indices by neural network. What's the difference between linear regression and logistic regression? In case of linear regression, do we want to Okay, can I represent BC as C? Yes. What activation functions go with them? Exam question, if a network classifies 5 classes, what loss should I expect? Okay, that's a question that comes back a lot. Exam question, if a network classifies as five classes, okay, at the end, I have 1, 2, 3, 4, 5. And after the first iteration, yeah, what almost, what is the expected loss function of the CE, of the cross entropy? Matteo is right. Thank you very much. And you don't need to dive into more than that. I know it's important, it's interesting, and I prepared for you a Python script that discusses it, that shows you how it's done, like that it actually happens in practice. But all you need to know is what Muhammad just written. If you're asked this question, you do minus log of 1 divided by the number of outputs, and you can continue, and you save yourself about 2 minutes of exam, which is amazing. Okay, you don't need to think about it. Yes, also only for random initializations, of course. Yeah, just remember it. Of course, if you want to, we could discuss it, but it has quite complex math behind it. The question is, if I have 5 outputs, what is the expected loss value after the first iteration? I do 1 forward pass. What is the after random initialization? What is the expected lost value? And as Yassin said, or many other people said before, okay, because each one of these logits will have on average will have a probability of 0.2. No, definitely, something like if it's not random, like if it's, of course, you put it to 0, all of this will be 0, and then, of course, this.
Sorry, Dan, can I ask a question?
Of course.
What if it's a binary cross entropy with 2 classes? What would the expected loss in first iteration be?
If you have 2, so basically, I think this would be 0.5. I haven't checked it myself with this specific binary cross entropy with a single neuron, but I would assume that this is the case. Anyway, if this is asking the exam, this is what you write.
Okay, so not minus log 0.5, just 0.5.
Yeah. No. Minus log 0.5. Definitely.
Okay.
Yeah, definitely. Because it's like the logit of the network, yeah, the network of the network will be 0.5 on average, not necessarily, and then we push it in the log function, and the log function will give this.
Mm-hmm.
And in the loss function, log function.
Right, thank you.
Okay, let's see. Oh, what else? What functions do we know that share variables which are element-wise? Okay. So what activation functions or loss functions do we know? Activation functions are known. Okay. No, the thing is that the difference between, for example, sigmoid and softmax, a sigmoid is element-wise, for example, and softmax takes into consideration the entire vector. Which is important when you do the derivative, because as we remember from the Stanford article, layers that have element-wise operation will have element-wise multiplication between the D out and the result, and the layers that have a vector multiplication will have vector multiplication. It's not on Piazza. I could share it with you later on, okay, if you want. Okay, let's continue. We have a lot to do today, and important stuff. Okay, let's get to them. One of the biggest questions that come every time, every semester, and it will probably come up this semester also. What is the difference between gradient descent and stochastic gradient descent? And it usually comes in a structure of, give me 2 advantages of stochastic gradient descent of gradient descent. You pick because we take the mean. Okay, well, okay, Ekaterina, you'll need to explain. Less memory required. Noise gradients have to overcome local. Juan, that's something that many people lost points for it last semester, and that's something I should actually emphasize. Not local minima, but poor local minima, because our problems are usually not convex and they have many local minimas. And when we converge, we usually converge to local minima. So it's either saddle points or poor local minima. SGD tries to approximate GT for the whole data set, which is often too big. Okay, so Benjamin wrote it correctly. But not really correctly, because GD could also be used with batches. What is the main difference? The main difference happens in the optimization step. Not necessarily less memory required. That's not true. To save computational resources, not true. Easier to compute, faster training. Faster training is not enough. Why is it faster training? GD, more GPU, not true. S2D will use less memory, not true. We do not need to store all the flows in the memory at once, not true. We use batches with gradient descent. In stochastics, we take into consideration only the subset of the training data. Okay, that's not an advantage. In terms of, that's a good question that I asked you guys, because all of you will lose all the points. In stochastic one, we take into consideration all the subsets of the in terms of saddle points that GD can overcome getting stuck in due to the noise updates. Okay, that's a good one. GD computationally complex, slow and use large batches, not true. SGD less computationally complex, not true. Faster, what does it mean to have faster? Uses many batches, use less memory. No, and no had noisy updates. That's true. I believe you got 1 point out of 2. SGD noisy updates. Okay, that's so what, Kevin? Sorry, that came out wrong. So, okay, what does it mean? Okay, mini batch. GD uses mini batches. You can use mini batches. SGD uses mini batches. Also GD. For SGD after every iteration. Thank you. Okay, Lorak is the first one to say that. SGD updates every iteration. This is why it's faster. Although the GD would have a much more accurate direction or accurate gradient, it will do after you finish the entire data set, basically after every epoch. And that's why it's super slow. It will never converge. Iteration epoch, thank you, Burak. We'll add the weights after each mini batch. Thank you. SGD process data points one by one. No, we could use batches. So Utku, no. Okay, so pay attention, okay? Pay attention. The SGD does it every iteration against every epoch, which makes it faster or feasible to deploy. And it has more noisier updates that help to overcome local minimas and poor local minimas and saddle points. Also, it was shown later on when we discussed batch normalization that a bigger batch than 32 actually leads to poor generalization. So you do need the noise. You do, because all this, what a neural network does is try to minimize the loss function for the training set. So you have to have the noise for generalization. Otherwise, it doesn't work well. Can you please repeat the part of the noise? So SGD uses a subset at each iteration. What GD does, GD, let's do, okay, maybe I will write it for you on the, wait. So for I in epochs, so range of epochs in Python, and then you do, so what happens here in GD, yeah, you do a out, which is forward, and then you do loss or loss 2 plus minus plus minus you do loss of the function, okay, and you do the backward at the end out of these 4, like loss in PyTorch, okay, you do it outside. When in SGD, this goes inside the for loop. How can GD use batches? Like this, you accumulate the gradients. Basically, you just accumulate them in the same place. And then you divide by the number of batches, the number of iterations. And then you have you have the average, or basically you'll get the exact gradient across the entire data set. And it can be done in practice, but it's irrelevant because, well, it does it every epoch, and epoch could take an hour to run. And that's something that I'm glad that we discussed, because this is super important. So the noise that we have is basically when we take only stochastic, or we take the optimizer step according to a small batch, it will not be according to the entire data set. So it will for example, yeah, we have 10 classes, and in our batch we have only images of 4 different classes. We have batch as 4. So we do a step towards that will help those 4 classes, but all the others, it might be irrelevant for them. So it reduces noise. It introduces some error to them. It is not in the direction that they need to go. Poor local minimas, for example, we have the loss curve. So we have here, and we have here, and we have here. Okay, this is a poor local minima. This is a good local minima. This is, you could have even a better here, right? But we might not get there. So this is a better one than this one. Usually in our problems, specifically with batch normalization, the curve will have less dramatic differences. It will have this, and this, and this, and this, and this, and this, okay? All local minimas. This is poor, this is okay, this is poor, this is somewhat okay. Are there any advantages of GD? No, there are no advantages to GD besides the fact that it has a more accurate gradient, but it's not an advantage in deep learning, and we've already shown that it's just not a good thing to do. Please correct me if I understood. GD updates after epochs, while SGD updates waits after a iteration, which leads to noisy updates, avoiding saddle points or poor local minima, and it's converged towards global minima. No. Gaur, you lost half a point here. We definitely don't say we converge to global minima. This is definitely not a case. We have many minimas. We just want to converge to a better one than the poor ones. And that's the task. Global minima is a task that is basically impossible to reach. Every batch, Jonas. We never use one, like, in most cases, we will never use one sample in a batch because that's super noisy. That's already super noisy for SGD. It will take forever, if at all, to converge.
So if we have the exam question like write 2 advantages for gradient descent and 2 advantages for SGD, what would be the answer to write? The short sentence answer.
Advantages of SGD is noisy updates to avoid poor local minimas and saddle points, and faster training because optimization step at each iteration versus each epoch. That's like the full answer. And PROMVAT, yes, better local minima, yes, that will be a better solution. And I know it's like going into fine details, but I expect you to do that because I expect you all to be the best deep learning experts ever. and it's important to know what you're dealing with. Is there any advantage of using HUD at all? No, GD is just here for theoretical understanding of what's going on. It is never used in practice, never. Like, for example, if you wanted, you could do, if you want to do the entire full batch, you will already go for Gauss-Newton, not gradient descent, right? SGD may converge to linear, but it will take longer in time. Muhammad, definitely not. GD takes, you will have to wait for the entire epoch to do a one step. Of course, you could mitigate it with a much larger learning rate, but to score a perfect learning rate for that is a mission impossible. So definitely not. So SGD is faster because it will do every iteration. So it will go at the amount of time that you're spending watching your model training, SGD will converge at some point, GD will never converge. Also, when it comes later on for Gauss-Newton, many people last semester, I had a question, I had to correct it about Gauss-Newton, and many people said that it will converge faster. And Gauss-Newton, like they wanted to say, it takes, or maybe it takes more. They wanted to say what is disadvantage of Gauss-Newton. It takes longer to train, which is not true. It takes for each iteration because you have to calculate the entire data set or the Haitian, the inverse Haitian, which takes a long time, but eventually it takes less steps. So it's something that is very, 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 very important to note. So the batch sort of comparison by was updating all the every book is too slow to update every sample, and not batch sample would be too noisy. Yes. So SGD may converge to better local minimum. Yes, faster. I think Gaussian only converge to its first step. Oh, Kyle, that's a good. I haven't gotten to there yet. A Gaussian only converges the first step for linear and convex problems. It does not do that for deep learning problems, and also think that people lost many points over last semester because it's just not true. If you said it converges less for linear problems, it converges one iteration, yes, definitely, because that's the true statement, but it's not true for all statements. Okay, I think I've answered all questions about that. I hope this is clear. What is the difference between SGD and GD? Let's see, what else do we have here? Regularization. Should we talk about regularization now? Or optimizer, and then I'll go back to regularization. This is also important. Okay, this is all the optimizer now. So, so it's already here, so I will do it now, okay? But it's not in the right order. Okay, so this is a thing we call either L2 or L1 regularization or weight decay. From my research, weight decay could also be is used as the same thing, as the same way as L1 as L2 when it comes to stochastic gradient descent. And this is how we ask you about it. So weight decay and L2 regularization, the same term. Apparently, when it's applied with Adam or something else, it is used a bit differently, but we didn't teach you that at all, so we're not going to ask you about it. So as far as you're concerned, weight decay and L2 or L1 regularization is the same term. Okay, that's important to note. Why is it called weight decay? What does it do? Okay, do we have the gradient here? I think we do. So basically how do we apply weight regularization? We take the loss function at the end, and then we take all the parameters in the network, all of them, all the 25 millions that you have, and we sum them up at the end. Okay, why does it help us? And we have, of course, this term to mitigate. Okay, why does it matter? Why do we want to do that? So basically what's important here is not what happens at the loss function stage, it's what happened at the derivative stage. And what is the derivative of a dl of some dw l input output? what happens here? So basically, it will have the exact same. Each weight will have, for example, it's a fully connected layer. Yeah, so it will have the the relevant xi, whatever, and the relevant d out from, I don't know, let's just call them i's. I don't care. N, which n? Here n represents, okay, here n represents the number of parameters. I know, it's confusing. I'm sorry for that. You could also do, instead of the sum, you could do p out of param, for example. Okay. Okay, so basically we'll have and of course we'll have the derivative of the weight. Let's say this is just a fully connected layer, and then we will have the relevant weight with this part, with the weight decay coefficient. And we will have, I think, because this is to the power of 2, this goes down, and usually we have a half here, so it will have the weight itself. Okay, why is it important? Why do we need this thing? And of course, then in the optimizer step, it is wrapped with the learning rate. So this is what we have later on in the exam, and the formula that we have. But why do we need this? Because it pushes the weight. Basically, it tries to decay the weights. In order to minimize this loss, it needs the weight to be 0. Right? That's what it tries to do. It tries to push it, whether it's positive, whether it's negative, it tries to push it to 0. And because this is the only way it will manage to overcome this problem. And that creates regularization, because we need the weight to not be 0. But on the other side, there is some other force that tries to push us to 0. So this part will have to find a way to overcome this problem. This is regularization, like in dropout. When we drop out neurons after randomly, the network will have to try to understand how to overcome this problem. Like it's losing soldiers in the battle, but it needs to find out a way to still solve the problems with the problem at hand. So eventually, if I'll just do it from the top of my head, I did not memorize it. I think that the derivative will be theta, let's say k plus 1 equals theta. This is just gradient descent, yes? Theta k minus alpha, the derivative of L, blah, blah, blah. This. Okay, any questions about that?
Yes, I thought that L1 regularization is the one that tries to push the weights to 0 and enforce sparsity.
Both, no, that's a different thing. Okay, there is a difference between the L2 and the L1. Both of them try to do it with 0 to push the 0. L2, as we say, and you could find this thing on Piazza, the discussion. I think Jinkung gave you a nice machine learning background about this. And the L2 will try to spread the burden of regularization over all the weights, while L1 tries to pick, will send some of them to 0, or at least these parts, and will focus on specific features. Why does it happen? It is on Piazza. You're not required to know that. Okay, it is beyond this course scope. It's good to know. Okay, but both of them try to do the same things, to send it to 0, just in different ways. It's like it's the same way of if we have a grid. And I want the minimal distance between this and this, L2 will go this way, and L1, which is the Manhattan distance, will go this way or this way. We have many more options to do so, or this way, whatever. Okay.
So if there is an exam question to compare the two, is it correct if I say say that L2 tries to distribute the weights evenly and L1 enforces sparsity.
Yes, enforces sparsity. Yes,
Okay.
chooses features. Yeah. So the lambda theta should be as small as possible. Oh, Jakob. So that's a good question. Small as possible could be also e to the power of -8, but then it just doesn't do anything because it's just too small. It doesn't have any magnitude. On the other hand, it cannot be too big because then it will have too much of a magnitude and the weights will be pushed to zero and the network will not stop learn. Usually, as we saw in the exercises, it's good to have them in the range of e to the power of -4, e to the power of -6, and this is already fine-tuning that you need to do. Okay. For example, also, I like this one. Some of you also already answered it earlier, but can you now phrase in the chat or for yourself, if you want, what is the definition of regularization? Take half a minute or a minute. This is a question that will come, definitely, it came in every exam. What is the definition of regularization? Until it's not enough. Abril, if you combine all of your answers together, that will be enough. Lily, your answer would have been accepted. Okay, Evgeny, you're just missing the how. What does it do? You're just missing the first part of the answer. Jonas, without the regularization, we divided the loss by n. No, because it's like using two different losses. Generalize better. If you say that, you lose. You will have half a point out of 2. Kyle. Regularization, making training harder, more constrained. Try to write what you would have written to me in a week from now in the exam. Dominic, not necessarily, not just weight decay. Every regularization, if it's data augmentation, if it's dropout. Method that increase the training to actually decrease. Huang, I still don't see how does it do it. Any method that tries to decrease validation error, usually by increasing the training error. That's true, but how does it increase training error? That's just made two words that are missing. Make the training harder to increase the generalization. It's in addition to the loss function to prevent. Yulia, not just weight decay, I'm asking of any regularization. Reg is a method to enforce generalization on the model by adding constraint to learning. Okay, and method to enforce generalization. Still missing how it's doing it. Techniques to avoid overfitting. Okay, that's good. First of all, saying overfitting in generalization will give you points. You need to do that. Like that's the main point of. Many of you didn't say even overfitting, and it's like super important to say. Technique attempted to improve model generalization by adding weight penalties. Evgeny, again, not just weight decay. A technique to increase generalization by adding more constraint to learning, which constraint to learning, I see many of you say, so it would have been accepted, making basically the training harder, which increases training error and decreases validation error and tries to solve the overfitting, makes well train how to train extra parameters with extra parameters to the model, but Batuhan, no, definitely not. To train with extra parameters in the model, that's not true. Technique that aims to reduce the generalization gap, which restricts the training. That's to reduce transition gap, restricting the training. Okay, but you didn't mention overfitting. Make training harder to avoid overfitting and decrease validation error. Make it harder to avoid overfitting and decrease. Okay, Mohammed, that would have been accepted. Make trainings more harder by adding more constraint to perform better. Okay, Kasun, but don't forget overfitting. Makes training harder to combat overfitting and leading to better generalization. Yes, okay. Jacob, your answer would have been accepted. Regularization making harder, training harder, more constraints to the model for better learning to avoid overfitting to this file. Yes, Gao, good answer. Adding all outliers and inliers into consideration, eventually avoid overfitting. Kyle, I don't know what you're talking about. Are you referring to something specific? Because there are many regularization mechanisms that we know. Do we need to mention both, avoiding overfitting and improving? Yes. No. Dominic, I cannot know if you understand that or you're just repeating stuff that you learned. What I care if you understand the topic, and if you overfit, I want you to just say, I know that I overfit. That's the whole purpose of overfitting, and this is how we score this exam. So be careful. That's why I'm doing what I'm doing right now, because you won't do these mistakes in the exam. Technique that aims to prevent overfitting generalization gap by introducing to prevent generalization gap. That's Katerina. You need to reduce the generalization gap by introducing constraint, making the network less flexible. With that training, less flexible. I'm not sure what you're saying. With that training, gets harder and won't overfit. It's too messed up. Make training harder to avoid overfitting by adding more constraint to lower. Make training harder to avoid overfitting by adding more constraint to lower value. Increase training value. Okay, Amy, Amy. Sorry, that would have been accepted. Okay, so you see why we're doing what we're doing right now. Why is it super important that you try and score the exact keywords that we will be looking for, which are important. And why you should not start and writing long answers, because you could get lost with it very quickly, specifically under pressure. So good practice. Is often more or less the same as network memorizing the training data. Could be. Or, yeah. When asked definition of regularization, do we need to give examples also? No. If I didn't ask you for examples, you should not give examples. You could give, but it will not help you in any way, and you just take precious time that you need. For example, I would ask you, give the definition of regularization and give me two different regularization mechanism. I don't know. I don't find the word right now for that. Okay, I will write it for you. Just a sec. Reg, you could write reg because we could save you some time. We understand what you mean. Okay, easy stopping is not a regularization term, and it's good that you brought it up. It's not a regularization term. It solves overfitting. It's not a regularization term. Early trouble. Oh, shit. Right. Sorry, just okay. Let me write regularization, a mechanism to prevent or tackle overfitting. Prevent will also work also. Early stopping is not ask yourself, Matteo, is early stopping answering to the definition of regularization? Does it make it harder to train? If I overfit my network, do I go into early stopping to solve this problem? No, it's just a mechanism for me to do automation of stopping the network when it starts overfitting. Exactly. So it's not a regularization term. Oh, I answered only to Helena. Just a sec. Please avoid sending me private messages, because then I do these mistakes. You know what? It's not correct. It's not a regularization term. But if you say in the exam and you write to me that early stopping, and then that you show me that in the slides it's what's written, then yeah, you could get the points, because, well, I cannot argue with what the official material is. It is not a regularization term, though. Okay. But if, of course, you can prove from the slides, even if it's wrong, that is given for you, you can do whatever you want. So, or shoot, I'm not sure. No, definitely not. It could be dropout, data augmentation, weight decay. Is normalization of the data when I load the data, is normalization of data, is it data augmentation? Is it regularization? Normalization, yeah? Like when I take the mean and the STD and yes, it's definitely regularization, because then you have then the network cannot memorize, or it's harder for it to memorize a bigger data set. So data augmentation, adding more data is also regularization. Yes, adding more data. Yes, it's like data augmentation, right? It's just basically adding more samples that the network would have to deal with. Is expanding the world that it could learn from, but it would have to generalize to all of them together. Okay, let's go back to where we were. Okay, this one was in an exam once, I think, right? Was it here? Where is it? Yeah, this thing. For convex problems, or to local global is for strictly convex. Yeah. What is important to know here? That was for you needed to memorize it in one of the exam. I find it bad, so I don't think it will come back this exam again, because it's just a stupid question. Again, please, why is normalization no, that I ask you, Jonas, normalization is not a form of regularization. I wanted to ask if normalization is regularization. It's not. Bagging is, yes, it's done, because it's part, like dropout was the evolution of bagging. Correct me. Reg methods, L1, L2 reg, which is weight decay, dropout, data augmentation, bagging, and ensemble, which is dropout, batch norm. Okay, batch norm introduces regularization term, like stochastic gradient descent introduces regularization, and which is this noise. I wouldn't use it as a regularization term. This is not the purpose of it. That's a good point. It could introduce regularization. It is not, when I overfit, batch norm is not where I go to try to solve it. But it introduces noise. Why? When does batch norm introduces noise? Who wants to answer? Because it's already discussed. Just this question, not any other thing about batch norm.
The mean and variance are calculated only for batches, and that causes noise.
Yes, that causes noise. But when it introduces bad noise, like proper regularization, like a small, okay, that's basically the answer. With a small batch size, it just cannot. And I can ask you that, why does small batch size doesn't work well with batch norms? And it's because it does not manage to capture the distribution of the real data sets. Okay, and when applying realization, which is supposed to make training harder, does this implicitly always mean we need to train longer too? Kevin, yes. Why is that? Because it needs more time to generalize. It has more, it is harder for you to train. So yes, you will definitely need more. Okay, this question that I wanted to discuss, all I want to discuss here is this part, and this series of learning rates, basically. What is the mechanism? How do we call this mechanism that implements this constraint? It's a practical mechanism, yes? It's not a mathematical one. Like early stopping. Who knows? The question is, I have a series of learning rates, positive step sizes, and it has to answer to this. Thank you, Benjamin. Learning rate decay, LR scheduler, all of them are accepted. This is if you ever implement a training process pipeline without learning rate decay, I will find you like Liam Neeson. Okay, I hope that's clear. Last semester we had a question about that. It's a super important mechanism that usually is forgotten. Okay, I think we go now to. Okay, so we go with momentum, and then we go. Did you guys touch Nestrov this semester? I'm not sure. This is from previous semester. And RMS prop, of course, you have, and Adam, of course. And this we'll discuss and use the methods. Okay, let's just discuss optimizers. Can someone tell me if you did Nestrov? Okay, you did. Okay, so let's start with momentum. Okay, momentum follows this physical notion of accumulating momentum when we have a very nice slope. And the thing is, why do we want to use momentum? What is the, okay, that's a question that comes up every semester, almost every semester. Can you give me the, okay, well, at least why would you want to use momentum with SGT? What is the advantage of using momentum? You can give me two reasons. Okay, now Gao, I want you to note for faster convergence. I want you to say why. Okay, usually I will say why, but we expect you to also to explain this shortly. It's never enough to say just for faster conf. It doesn't show that you know and you don't know what you're talking about. Momentum helps overcome not good local minima. Okay, that's good one, Tim. Faster convergence. For this, I'm missing a little bit. Converge faster and might help overcome. Yes, that will probably get 1.5 out of 2. Helps not to get stuck in saddle points. Okay, get over plateaus. Yes, to increase gradient step size in recurring directions. That's not the advantage of this is how it's doing it. Overcome poor local minima. Okay, scales the gradients. That's not an answer. Helps avoid saddle points and increase landing rate direction. To don't overshoot. You're gonna overshoot. That's not That's not a good answer. Sorry. Accumulate prev gradients for faster convergence. Yes. Okay. Accumulate previous gradients for what? Avoid zigzag path. It will do the zigzag path just faster. It doesn't solve it. One faster is some directions and other slower. That's RMS prop. Accelerate convergence by adding. So you think that's not a good answer. Sorry. Accelerate convergence by adding momentum. The term that cumulative function of previous updates to influence current update. Yes. No. I hope I pronounced it right. No, Hahila. That's a good answer. Accumulate gradients leading to faster convergence and overcoming bad local minima. Jakob, perfect answer. Thank you. It helps the learning rate to better adapt it to distance of the optimum. It helps the learning rate to better adapted to be better adapted to the distance of the optimum. No, I don't. It's not a straight through answer. Con faster when the gradient is showing this the same direction. Convergent faster, not convolution faster when gradient is showing the same direction. Okay, that could be accepted. Momentum keeps track of recent weight updates, which helps us to do larger optimization when recent gradients are in the same direction. Yes, speeds up learning faster along direction of strong improvement. Okay, strong improvement, I would assume that you mean the gradients, and then I would accept it, okay? Because, okay. Yeah, but I would rather you to say accumulating the gradients in this, or in directions where speed up learning rate if gradient point of the same direction, keep the deer of gradient to escape local. Again, not local minima, poor local minima. Local minima is something that we try to find, and that's a fine detail that I want you to make sure that you understand. Using history of gradients to achieve faster convergence, Vlad, that would be accepted. Smooth noise updates, that's RMS prop. Could you also give a perfect answer for this question? Dampens out oscillations, that's RMS prop. Faster conventions because it accumulates previous gradients, meaning we have faster horizontal jumps over slower vertical jumps. That's RMS prop. Sorry, kind of missed it. What was the question? Would momentum make any sense for just GD? GD would never make any sense, so no, definitely not. Accumulate prev gradients so that it converges faster. Accumulate prev gradients so that it converges faster in gradient points in the set. Yes, that's usually the goal. That's usually the answer that's being accepted. Let's try. Accumulates SGD plus momentum. Might have some typos, so forgive me for that. The one is over local minima is the lecture that was example where it ended up in the worst local minima. So it's okay to say it overcomes poor ones. Usually it could help you over. It could help. So in some cases it could be wrong. This is why we have other optimizers. We don't really use this, but it would help you to overcome saddle points, and it could also help to get to better local minima. On average, I guess, nothing here is pure math. It's all what I gave you. My answer includes both answers, right? Like both of the advantages of using momentum. Now, for many semesters, I argued that this one is not the proper weight sum, but well, I how do you say? I got off my tree. Oh, what's going on? Basically, this because it's not as we know it from RMS prop and Adam, it's not really the same formula, but you could say weighted sum, which is also okay to do that. Okay. Any questions about momentum? Yes, that's a good question. You should know the formula. For all of the optimizers, usually we will give them to you. I find it useless to ask you for formulas because you could always just Google it today. It's just meaningless. But I'm not the only one contributing to the exam, so I cannot be sure what's going on. Okay, let's discuss Nestrov. Look, Nestrov was what is first order method? I will get there, okay, when we get there. When we get to RMS problem. Okay, so Nestrov was asking one of the exams, you needed to explain it and you needed to give the formula. That's why I'm asking you need to know it. What it does, basically, the idea, it's quite an interesting idea, is to do two steps. One is to do just the original momentum, and to do the original momentum idea is to basically, if you're here and you want to get here, and you do the step, and then you get here, you say, oh, I'm not really at the loss, so let's find from here. Let's find the loss. So you have to do another back. You have to do another forward and back, blah blah blah, and then you could mitigate the point from here and just go here instead of doing this zigzag. Also not used in practice. Many other better ones. But the key words that you need to know here is look ahead. Okay. A Heun method I'm not familiar with, so I can't answer that. Rungekuta also not familiar with. I don't know. Okay, but the thing that I want to focus on are like, did you talk about it in the lecture? Because did Nisna mention this? At least Heun or Rungekuta. Maybe I haven't looked at the slides. Okay, I'm continuing. Okay, this is discussion that is not relevant here. Okay, RMS prop and Adam. These are two important ones. The RMS prop was the first one to introduce the idea of using the second order momentum or second momentum. Okay, which is different than second order gradients, the second order derivatives that we see in Gauss-Newton. Here it's the momentum, this probabilistic term that which all you need to know is that second order means variance, first order means mean, like the average. Okay, so basically what we do here is it uses the second order momentum, not moment, which is important. I also mixed it up now. Moment is this, it's this term, and second moment is variance, and that's what it does here with this. Why is this the variance? We could see it later on here in the page. I've written down for you what is the variance. This is the variance, and we assume that we have mean of 0, and basically ex to the power of 2 will be the variance. And this is why, and we take, and this is the running mean. The purpose is the running mean. So the running mean of the power of the x to the power of 2 is the variance. This is why we call it second momentum. It's not accurate at all, but this is why it's called second moment. Okay. Oh, you were right. Didn't see. Okay, let's finish the optimizers and then we'll have lunch break. Okay. I didn't see that we already almost at 1. Okay, sorry to keep you. It's time for a beer. Where is your beer? Okay, that's important to think about, to know about RMS prop. And RMS prop, what it does is basically dampens. This is the thing that you need to know about RMS prop, damping the oscillations for high variance directions, basically mitigates the problem when some directions go very, very far and some weights have a smaller gradient, so it brings them somewhat to the middle, and so that both could learn at the same time, which makes learning faster. Then came Adam and said, oh, let's just use also momentum, and this is Adam. So it uses second order moment. Yes, second order method are the Gauss-Newton ones. I know it's so confusing. So it is what it is. Now I want just to, unless you have some specific question about RMS prop, let's just move to Adam because it answers all of it. Adam, what it did, second order moment corresponds to variance and first order yes, and first order moment corresponds to the mean, the average. You could see it here. If you go to page 23, I explained it here, okay? The first order moment, a second order moment, and so basically what David, what you're referring to is a specific case when Y means big oscillations and X means small oscillations. So the division will be bigger, like as you see here with the momentum thingy, it will just, if we have this and this and this, so this will be cut by a bigger number, this will be cut by a much smaller number, so they will mitigate the difference between them. That's just the point. Okay, with Adam, they basically took momentum and RMS prop, put them all together. Quite easily, this is just how it's used. Before the so basically we use both momentum and the RMS prop in the same place, okay, and use in the SGD format, but it introduces two different more steps, which hour you mean we meet afternoon? I think we finish now, and we'll start about 1:30 or something, or 1:20. Yes, I will upload this on Piazza or YouTube, basically. Okay, so basically, the thing I want to touch. Why do we use the bias correction? If you remember what bias correction is taking these terms, okay, which is important to note. If I go deep inside, this is an index or iteration. And this is an exponent. Someone needs to fix this. This needs to bring this down. As like the sooner as I can, you know, try. It needs to process, needs to upload, and then Maybe tomorrow it will be done. Okay, so this is important. This is exponent. Okay, so that's the point, that this becomes mk plus 1, or returns to the original one as we go more and more iterations. So we continue with the pipeline. Okay, so at the very beginning, this will be mitigated from the 0, and then basically, if this is mitigated, we divide by this, so this is gone, and we're left with this. Oh, so if this is very big, right, this is gone, and this is gone, and we're left with this, and this is what we're left with. And as we go more and more in the pipeline, in the for loop, we will get mk eventually. So this is just a simple solution to solve the bias correction, that solves the problem that that it's very biased to 0 because mk and vk are initialized to 0. So the steps are very, very, very small, and we want to solve it for the very first steps. So that's the thing, Noah. This one changes as we go. This is exponent, and this is, so beta stays the same, but if to exponent, like 0 to the power of 9 to the power of 100 is different than this, right? But it's this, it remains the same, the beta. Beta doesn't change. So why does, okay, let's just take this, shall we? Okay, if you want to do this, so basically beta 1 mk plus 1 minus beta 1 this, okay? I just do x, whatever. Okay, now let's divide by 1 minus beta 1. Okay. So can I remove these to this is 0, right? This is the initialized to 0. So by, and this one is this is divided by this, so this is gone, and we're left with this. Yes, beta is chosen as a hyperparameter, never changes. Usually it's 0.9 for beta 1, 0.999 for beta 2 for the gradient. But is it understood how it solves the problem?
And if there would be an exam question about this, what would be like the short answer to give, the one sentence answer why we do this?
The variables mk, m, and v are initialized to 0, meaning that without it, meaning that the first iterations are very, very, very small, or the changes is very small to non-existent, and that's mitigates it for the first iterations. That's basically it. It solves they are biased to 0. MK, they are biased. The first iterations are biased to 0 because the MK and VK are initialized to 0. That's all you need to know. Okay, guys, this is the end of this part. We could also go to Newton method quickly and then go to lunch if you want, or we could do it later on. I think we should just do Newton because it's 2 minutes. Okay, so the Newton method and its variants, like the Leavenworth-Marquardt and stuff like that. Yes, please. Yes, I don't know to which part of the the question you referred to. The idea behind the very I wanted to show you the thing about Newton method and how Newton method, or we always say that it utilizes. You need to memorize for Valad. You need to know them all by heart. It's not a lot. Memorize them all. Not from the Newton method. Newton method, you should know all the Newton method. Like this. Okay. Any other? Yes, for example, you should memorize how to do receptive field. and you should memorize how to calculate the spatial size of convolution layer of the output, stuff like that. You know what? Let's just continue after the break, okay? I'm also a bit tired, and I see that you have many other questions, so I'm going to stop this now. Zoom. Okay, so we left at the Newton method before you guys bombed me with questions. So let's get back to Newton. Now, Newton is a very interesting way to deal with optimization. Basically, the Newton algorithm tries to take the curvature of a loss function and to use it instead of a learning rate. So one of the advantages of using the Newton method is that we don't need the learning rate anymore, which is incredible. Now, Newton method, before I dive into it, I'll just say it again. It will converge in one step only for convex and linear algorithms. In deep learning or any other complex problems we might want to use it. For example, remember that we managed to squeeze the entire Cypher10 dataset onto the RAM. And let's say we managed to do with the entire dataset some manipulations like convolutions or whatever. It will not converge in one step. Like it would take a much fewer steps. The problem with Newton method is this Hessian matrix, which the inverted Hessian matrix, that only a few people mentioned last semester that it is an inverted Hessian matrix, and they got full points no matter what else they said, because that's the most important thing. That takes most of the time. So basically it would converge faster in total, but each iteration will be longer. Okay, which is very important to note, because why would it be much longer? Because this takes a lot of time to compute, and we really compute a Hessian matrix, which is like multi-dimensional thingy. This is why we have all the other variants that don't do that, because Jesus. Now, the thing that you need to know about these kind of variants of the Newton method is that we only need the Gauss-Newton. The rest is just for you to know. Matthias Nissner really loves these because he deals a lot with 3D reconstructions, not with deep learning, and there it is used a lot to minimize a loss between, for example, when you do a panorama, right? And you have patches of images, and you need to combine them together, align them together. Here it's used a lot, and it works superly well. In deep learning, it is less used. And the point is that you need to know is why it is not used in practice. Now, for example, if we have the x2 function, yes, for example, there is from 2 years ago, there is this question, very nice one. You begin with x equals to 5 and learning rate equals to 1. Right, and you need to immediately show that this will just overshoot the minima and will just go like this and will never stop. And we see there that with the Newton method, it basically takes advantage of this. How do you call it in English? Like the derivative, the slope. But this, yeah, but the line that go. How's the line called? I don't remember. Anyway, it takes this instead of the derivative of the learning rate in some fashion. Tangen, thank you very much. Yes, okay. And manages to converge in this specific case in one single step here. That's an amazing idea, which we cannot really use. So for example, the last semester's question about that was give two disadvantages of the Newton method. And people said, takes a lot of GPU. That's true. Why? Because it doesn't work well with batches. So you have to load the entire data set. So it is very, very inefficient computationally. And it is, each iteration will take much longer. If you say that it will converge, convergence will take longer, that you would have lost a point, because eventually, if you could use it, it will converge faster. I think so, yes, but we always like this is what we do always with unconvex functions, right? Where like we bound them into differentiable area, right? And then we do it. So that's what we mean here. So it's not really a can you repeat the iteration text convergence? So convergence overall it will be much faster than using the original deep learning with SGD and the variants, like Adam and stuff. But each iteration will take longer because if we just use the Adam or SGD with momentum, there are no much calculations going on there. If you need to do the Hessian, you need to calculate the invariant Hessian metrics, which takes a long time to do. Okay, and on a computer, also by hand. And this is why these two reasons are the reasons that it is not used in practice. And this is what you need to know. Yes, Benjamin, that's exactly, and this is exactly the solution that would have been accepted last semester. Just many people did not say that. They said it would have just been or faster or longer. And it's what we're looking to see is that you actually understand. It's not just you say, oh, Newton methods is faster. No, you understand what you're talking about. That's what we ask you in an exam. Okay, and that's why this fine detail is important. And I felt it is important to note. Again, the rest is just for you to know if you want. If you don't want to learn for the exam, do it. If you don't, doesn't matter. We will not ask you about the 11 mark quadrant. Maybe we could have asked you, what of the following, the multiple choice question, what is the following a variant of Gauss-Newton? And you would give you RMS prop, Adam, and this, okay? So that's like the worst that could happen. So this is why I'm not gonna talk about this anymore, unless you have a specific question about the Gauss-Newton and why we don't use it. Otherwise, okay, remember, yeah. That's actually a good thing that I want to discuss. Remember that in scalar notation, we're discussing here, this is, yes, if we have f of x, yeah, like, okay, f of x of theta. So this one is f tag, and the Hessian is 1 over f double x and theta. Okay, this is in scalar notation, and we asked you that I think one of the exams, and so it's good to know how to project it into the scalar world and not into multiple dimensions. Okay. Okay. Why does it not work with mini patches? Because it needs to take the curvature of the loss function. And with the other optimizations, you're doing an estimate, and here the Hessian needs to know what is the curvature in order to be calculated. So therefore, you need the entire data set because the loss function is over the entire data set. Okay. When you do, like when you have this graph, with all the minimas and stuff, this is why you need that, and it doesn't work well without it. This is why it's not using deep learning. But in other applications, immediately that would be your go-to algorithm too, if you need to do some iterational algorithm. Okay, so we're going to training neural networks 1. Let's see if there is anything here that it's important. Okay, so that's something can't we treat each individual mini batch as a data set? No, but then it would not converge well. It will just not work well with Gauss-Newton. It's just not the purpose of it. That's why you have the other ones. Okay, look. Okay. Okay, the thing is that I want to discuss here is this terminology, which I completely hate. I find it super counterintuitive, but this is the literature. So I cannot tell you what is overfitting, what is underfitting. For me, overfitting is really intuitive, underfitting really intuitive. Bias and variance, you could make my life harder when you write it down in an exam. Please don't, okay? I will not ask you about bias and variance in the exam in this context of underfitting and overfitting. So just please avoid doing that. Maybe we should, I think we talk here about overfitting and underfitting, so we'll get there. Let's see. Okay, I think that now we're going to discuss, okay, the splits. That's actually a good topic to discuss. Okay, so the known splits that we know would be something of the sort, right? Like if we take a training set 60, 20, 20, or 80, 10, 10, very, very common you would see in practice. One question that I like to ask about in exams, why do we need the validations? People say, oh, okay, we said that if we add more data points to the training, it is used as regularization. It will prevent overfitting, and minimize the generalization gap. Okay, so if this is the case, why not to do it always? Well, right after you find the fine-tuned hyperparameters and stuff, why not just train on the entire thing? Who can tell me why we need the validation sets and we cannot just merge it into the training? Thank you. Kevin, you got 2 points. To see how good our model is able to generalize, very good. For hyperparameter to tuning, no, this is before, I just said that. Maybe to have a confirmation that it really generalized, yes, exactly. Sanity check to tune model architecture, no, that's not the question. Hyperparameter, no, we need to do validation to set tune hyperparameters again during training. After we did the parameters, to check generalization, okay, we're going to have generalized model with the real data. Okay, that's not phrased well. To tune our hyperparameters and see if the network generalized. Tune hyperparameters, again, it's during training, not irrelevant here, to see if the trend can that's what I'm saying. You know, you hear something, you see, when we use a validation, we're not even referring to the question, and you just throw at me with everything you know. No, don't do that. Okay. Then the test set result would be biased. I wouldn't say so. To test generalization, did you ask what to use a validation? After training. No, not like after, during training. Lily, I think you guys misunderstood the step of hyperparameters tuning. You first find hyperparameters and then you train. So it's like 2 different stages. It's like pre-processing the images like this is the pipeline. I collect a data set, I pre-process it, I add data augmentation, I find the mean STD and I normalize it. Okay, and then I split. I need to see what split could be good. For example, a good example would be, for example, I collect a data set of, I don't know, dogs in the park during nighttime and during sun. And then if, for example, I just split the data, take 80% first of, like the data is sunny and then nighttime, and then I just daytime and then nighttime, and then I take training only from the test from this daytime part of the data set. It's very, very wrong, because it's like it's not the same distribution as the test and the validation. Okay, so this part of first finding the proper sets and tuning hyperparameters comes before training. When this is done, then we train. So basically, it doesn't happen at the same time. The validation during training is there for me to have a sanity check, because I cannot guarantee that I don't overfit, and I will lose so much time if my training loss goes amazingly well down, but then I test it and it's, oh my God, what the hell is going on? Okay. I really wonder where this point comes from, because many of you just say that, and maybe that in the lecture they just didn't distinguish the two steps, because training and setting hyperparameters are two completely different steps. You use the same data set, right? Like you take a smaller data set and small validation to see what overfits less, basically, and then you take these and try training. Since the model proposal, the validation is used to think like early stopping, there is some effect on model training from the sets validation. Okay, so Rog, your answer is correct, but it's too long. If you write that, you will lose time. Okay, it's just losing time. Try to make it more concise. Try it again. You could do it here, or you could do it on paper. Try to phrase it again. But during training, one training pass is meant. No, I mean the training process. You don't, like, usually you don't adjust hyperparameters during training. I don't know where you got this idea from. It's usually not, it's done in practice when you, for example, your model converges to higher lane rate. Eventually, you thought you found a good hyperparameters and it didn't work. So then you do it again. You go back and tune them, but it's not happening during training. They are fixed during training. Can you guys point me where it is said, because no one does that.
Sorry, one thing. So it's exactly on the page that you're at right now as well. There's like validation set and then hyperparameter optimization. Like that was the thing that threw me off a bit as well. Like, could you get more into that?
Sorry. Can you say it again? What can I dive into?
So on the page that you are on right now, like validation set, below that,
yes,
there is hyperparameter optimization. And that's, I think,
that's true. That's true, but I ask you
off.
what's happening. I ask you what is the purpose of the validation during training? Yes, the validation set, also the training set, is used for hyperparameters, but these are two different steps of the pipeline: pre-processing, right? Split, hyperparameters checking, training. They're just not connected to each other.
Ah, okay, I see. Okay, yeah, thank you. That makes sense.
Hyperparameterized optimization and tuning is the same thing. How is the validation? Wait, I think I missed some stuff. Let's see, mixing hyperparameters and weights. But for example, KNN, we tune K for the val. But hyperparameters, for example, for KNN is the K, and it's fixed before you start training, right? This is a hyperparameters. Hyperparameters are the weights are not hyperparameters. That's maybe someone's pointed it out here. They're not hyperparameters. Hyperparameters are learning rate, weight decay coefficient, hidden size, all the things that we did in the exercise that are fixed before you start training, right? That you send it the H param to your model, and then it fixes them and uses them to train. That. Okay, let's see. Someone sent me a, okay, shit. But more than if the question asks what is done during training, then it's wrong answer. If it's just what is the usages of validation, then yes. I asked what's happening during training. Okay, what is the difference between the data used for check overfitting with effect on both training, and therefore we need to separate validation? Yes, Rog, that's good. I believe they refer to the 6 slides set from lecture page 17. A screenshot would be nice. Actually, I just don't want to go there right now. It will lose too much time. Hyperparameters are set before training and set. Hyperparameters are set before training and set using validation set. They're set. I think all of you that ask these questions, please go back to exercise 6 and see what we did there. Okay, so we use train and validation set to find optimal hyperparameters, but the purpose of validation during training is checking the transition progress. Lily, exactly. Maybe a better way to ask during. but I don't want to training run. I just want. You mean because in exercise 6 we reiterated it all over again and again. But no, that's not how you do it. You find set of parameters, and then you start training for 4 days in a row, because that's what it takes. So it's super important that you, like, I don't know what. Yes, every training run would have its hyperparameter tuning if needed. Exactly, learning hyperparameter optimization. Exactly, but I ask what's happening during training, and that's the question. Like, hyperparameters is used during, as we did in exercise 6. That's true. Not during training. It is used before in the hyperparameters optimization step, and this is what we did. We did a grid search, right, and or random search. By the way, another question that we need to discuss. And then we took the hyperparameters we found and used the real data set, the big ones, to train. Okay, that's the important thing. Okay, so let's, if we already discussed that, like hyperparameters tuning, let's discuss grid search versus random search. And there is I guess so. The Marcus is right. Although it, like, the last cell in the exercise was meant for you to just run once with the hyperparameters you found. And that's how it's done. You don't train 70, you don't have the hardware, you know, like if one training session would takes 4 days, this is what you do. You train, you say, oh, this didn't work, I need another idea. Or, oh, this didn't work, I need to retune my hyperparameters. That's true, that's the circle, but this is one training. By training, that's what I mean. Okay, now I see what you mean, Benjamin, would say one training run. So if you use the val set for training, the val set wouldn't be indicator for generalization anymore. Eunice, yes, definitely. Okay, I hope we managed to solve the problem. Okay, so let's see. So we said grid search versus random search. And the only thing that you need to know here is that random search is shown or proved, not mathematically, to converge faster, to find a good set of hyperparameters faster than grid search. Okay, that's what you need to know about the difference between them. So it does it much faster. And there are, later on, if for those who will continue to advance deep learning for robotics, for example, you will discuss a Gaussian, I think it's called. No. Bayesian like Bayesian method of finding hyperparameters, which does like something for reinforcement learning, some exploration, some exploitation, and yet it is shown that random search is just the way to go in practice. And that's what you need to know about that. There was a question about Piazza about this one. Ground truth error is just human mistake. You know, for example, we projected stuff not correctly on the image, or we misclassified stuff. It just happens. What can you do? This one I'm not discussing. I still don't know why it's here and why they keep still using it, but it is what it is. Unless there is a question, okay. I want to discuss overfitting and underfitting, apply smoothing function. Okay, a question that always comes back. Give me the definition of overfitting, gives me the definition on underfitting, go. It's one sentence for each. Yes, Tim, it is a very, very specific case that was raised in the Stanford course that no one discusses anymore. It's super confusing. We will not ask you about it. And specific case of misdistribution of stuff. Like it's a specific, there is a whole lecture about it. I'm not going to touch it. Okay. Okay, and for underfitting, I wanna sharpen my question. Well, I'll do it later. Okay, I'll do it afterwards. And we can chapter. Okay, overfitting is when the model learn the training example by heart and does not generalize well. By heart, I wouldn't do it. You just memorize, or doesn't generalize well to unseen data. For example, you need to add David. Overfitting, memorizing instead of generalizing. To unseen data, again, missing learning training data without generalizing generalization gap. Okay, again, underfitting model not learning enough, overfitting model memorize data. Okay, underfitting model not learning enough. I would say doesn't manage to, like it's true for one case of it. That's I would say I would go in the direction of doesn't manage to capture complex structures or relevant features. Often model cannot generalize underfitting model doesn't present training data. Doesn't represent training data is again a bit of a vague description. Like I would give you the points here, but I would go for the try again. Model is not complex enough to capture all patterns. Overfitting model is much complex that can memorize all the data and not learn it. So to generalize. Remember when you say generalize in the exam, please do to unseen data, although it is no, one can just assume that this is what you mean. Overfitting is when model learns to reproduce. Overfitting is when the model learns to reproduce the training set. And fitting is when the model cannot converge enough. Okay, that's not true because there is a case where it can. Like don't say with underfitting where the model cannot converge. Because one case of underfitting is when you just stopped training while it could still train, right? Both training loss and validation loss still go down. That's still underfitting. Yeah, I don't think we have it here, this image. Let's see if we do. No, we don't think so. Okay, never mind. Basically, when like you remember the image of underfitting, when there is this specific point of when we did early stopping, like there's a specific point where the training set validation error starts to diverge, and then this is what we call underfitting and overfitting, and there is like this sweet spot between them. So underfitting has two cases basically. Again, and Lily, okay, I think maybe I've skipped some people. Let's see, underfitting model not learning enough, or fitting model memorize data. The training loss could be better. Okay, Vlad, underfitting, your description is not good enough. The model is memorizing the training set and doesn't generalize well. Okay, that's okay. Underfit, the loss is still decreasing at the end of training. That's one case. Again, that's why I would say I would go to the more generic case of just doesn't manage to capture sorry, it just doesn't manage to capture the complex idea, because also when it still didn't stop training, it still didn't manage to capture all the correct features or to converge the correct features. Or if it is when the model learns to reproduce the training set, it doesn't learn to reproduce the data set. Hendrik, that's not a good definition, because what does it mean? I understand that you know what you're saying, just work on the phrasing. Okay, I was with Lily. The loss is decreasing at the end of the training, meaning the model is too weak. Again, one case of there is a generalization gap between journals. Overfitting model cannot generalize. Underfitting model does not represent training data. Okay, underfitting model is complex enough to capture all patterns. Good. Overfitting model is much complex. Memorize all the data. Perfect. Mohammed, that was good answer. Overfitting is when the model learns to reproduce the training set. I just said that. Underfitting is when the model cannot converge enough. Okay, that's a good way to put it. Overfitting, when the model memorized the training data to be able to generalize from test. Test, not test, Mohammed, just Mohammed and Mahmoud, do use unseen data. Underfitting when model is weak to predict near the training test data. Okay, good. Underfitting, behaving poorly on training data. Good, that's a good definition, Gal. Underfitting, memorizing the training data. Memorizing the input data during training. The data is not explained well by the model. I don't like this phrasing, not explained well by the model. That's just so high and doesn't say anything, so vague, like literature vague. And computer scientists love these things. I don't. Model is memorizing rather than extracting patterns. Model needs more training cycles, still having training potential. Okay, Aaron, it's one case of the underfitting. Model capacity is low, that it cannot catch any pattern, but it would be accepted if I asked you just give me definition of underfitting, because it's one of this. Model lens noisy and just memorize the data. Is the validation crisis a silver fitting model? Oh, there's so many of this. Okay, I cannot do it all. Okay, I can't do it all. I guess I managed to give you some feedback of what should be and what shouldn't be. Remember that underfitting has two cases. One is when the training loss and validation loss just converge to a very high loss rate. And one that, for example, what would be a solution to this case when both of them converge to a very high loss rate? For example, let's say one thing is not necessarily going to be the solution, but it's a thing that should pop up into your mind. Oh, what could be the case? Most of the time.
We could add complexity to the model.
Sorry.
We could have a more complex model, like in that case.
Okay, more complex model could be, yes, that's one solution, exactly. Another solution, Jakob said train longer. No, I mean something like that. So this is train, okay, this is 0, and this is, let's say, val, okay? Both of them here. And I want them to go here. What could be a solution? One, complexity of the model, yes. Learning rate lower, thank you. Yes, perfect, that's what I meant. Okay, lower the learning rate. That's one solution to this. What would be the solution to this scenario? And this, let's say this is training, okay? This is val.
In this case, we can train longer and it will help.
Train longer, perfect. Okay, you're good. So you guys understand, very nice. Let's see if there is anything here that I missed. Oh yeah, definitely skipped a lot. We said overfitting, underfitting.
Sorry,
Okay.
what was the best definition for underfitting?
I saw here a few for that definition for underfitting. It doesn't manage to reproduce the training set. That doesn't say anything. Like I see that you understand something, but you don't manage to put it in words, and you should be able to put it in words. Or let's see another. Okay, as two cases of underfitting again. Oh, this is training. This is val. This is training. This is val. Two cases of underfitting. Okay, here converges to high learning rate. High loss rate or value. And here it just didn't stop training. So basically, the graph that we all know, right, is this. right? And we want to put, this is the switch spot, right, for early stopping. And so you could see it in the summary here. It's either this would be accepted because it's one of the cases, underfitting, or this, you could say converge to high loss value, okay? This or this. So choosing a different optimizer could help, but you have to explain why. And could you please explain early stopping? So early stopping is basically, we have this patience mechanism, right, that we train, and the training loss gets, we get to some points, and then suddenly, like, both training loss and validation go down, and suddenly the validation error goes a little bit up. And once it starts to converge, like sometimes it will do a little bit up, continue to go down, up, a little down, and suddenly it will just go up. And when it does this, it means that it overfits. Okay, and I want to stop, like, let's say, okay, it's overfits, I'll stop here, so it won't go, it will continue. A better way to do that, a better way would be just to keep, to just save your model, save checkpoints, and then it will always save when you get the lowest validation loss, always save, and then it will never save these, and you could just either stop it. You could always use early stopping, so it will stop by itself, so it doesn't just keep wasting electricity by running, or you could just stop it yourself, right? Early stopping is basically just the automation of that. So choosing different why choosing a different optimizer should help? Can you explain that?
Hello.
Mm-hmm.
Yeah, so because if both are high, that's the case of underfitting. It might happen that we might be having large gradients, so like RMS or Adams kind of damp oscillations. So that could help, like if we are going into different direction, if you're going into large variance of gradient directions. So in a way, in a way, these indirectly control learning rate itself. Like if you choose this learning rate,
I would go, okay, yeah, I would go to a precise answer, because we might have been stuck in local minima or saddle points, or poor local minima or saddle points.
yeah,
And then
yes.
choosing a different optimizer, bam, solve the problem. Okay, so this is why choosing a different optimizer could help. Okay. Let's see, any other questions about that? Okay, you could see here, for example, overfitting here, and underfitting, the one case of underfitting. Yeah, the second case. If this is considered high, so this is also underfitting.
Sorry, isn't the left graph?
Yeah, that's true. That's true. I didn't see that it's a train and validation. I just read it. Okay. This case, what could cause this case? Oh, I have two questions here. So before we move to this question, let me just read the chat. Maybe a dumb question, but when we trained our model in exercise, we often had many epochs of training and validation cycles. In each epoch, does the split between the training and the validation, does it get set new? No. So basically, no. Every epoch, we reshuffle the training set, because we want to avoid that the network would learn specific batches. We don't need to, we don't care about the batch because it doesn't learn anything from the validation, so we don't need to shuffle it. And it would have more a proper ground for comparison between each epoch. Although yeah, but oh my god, I'm missing. But we don't resplit. If we resplit, we train from the beginning. Does changing the batch size does anything to mitigate over and underfitting? No, that's actually a good point, LK. It was given like it could be, yeah, if like if you give me a batch size of 1, like eventually you will be able to converge. It will take much longer, but it introduces so much noise that you don't really converge to you don't really converge, so you could still keep going, so it's like underfitting. Yeah, I guess it could be unbalanced train. Okay, everyone that says about my question here that this is a bug, but what is the bug? It's like you asking me stuff on Piazza, like not reading the error. What is the bug? Okay, so training is set could be too easy. Could be, for example, if you have daylight and nighttime, and the training set has only daylight, and which are much more abundant in the training set, in the data set itself. So then, of course, it's much easier than. Yes, but Professor Nisna doesn't need to do the exam, and you do. Not a validation, validation, some distribution, cool, yes, okay, distribution, the distribution is the key here, very nice. Okay, different distribution. Can you tell us how parameter K in cross-validation influences training? Like the K defines how many values, okay, so the question is, can you tell us how many other parameters K in cross-validation influences training? So it influences the splits, right? And how you pick the best splits. And if you do a very large K, for example, let's say we have 100 images in the data set, and we say, and let's take, okay, 110, and then we take 10 for test, put it aside. And then we take K equals 100. It means the validation set has only one image. It doesn't represent anything, right? It has to have some volume to be able to represent the data set properly. So a big K would be a bad idea. A small K would mean the training set doesn't really represent. So the val data is not good. Representation of the data set while the training set is good representation. Well, I don't like this. Like the first part is good. Like the training set, you cannot assume it, like you cannot say anything about it. You just need to say that there is mismatch of distribution. You don't know what causes it. You need to go back to your pre-processing and understand. Maybe you did something that, for example, I'll tell you something from my experience. What I do in my project is that I train, and then, for example, there is error with too much, there is no enough memory, or I need to stop because someone else needs the computer and stuff. And so I keep a checkpoint, and then I reload the checkpoint and continue from the same place. And of course, I need to adjust the learning rate and stuff like that. But I just took code for someone else, and what they did, they had a bug that every time they loaded the data, they shuffled the entire data set and then split it. And I didn't notice it. So every time I reloaded my model, some of the training of the validation data leaked into the training, basically introducing more data, and they're showing me that my validation loss went really down, which shouldn't have. Like, Aaron, this is a very specific case, like about classification. Like, doesn't have to be classification. I wouldn't say the small batch size here is the problem. I would say that because it's not a really underfitting. So let's see, 100% training set, training data set. So for the left one, if I see something like that, actually, I don't know. Interesting. Like, what could be? Yeah, but listen, guys, batch size too small, you would see the training data curve doing these jumps, not the validation. Don't mix them up, because during training when we do the optimizer step, the optimization step, and we go with a lot of noise, you would expect during training to see this, right? Not the same case with the validation where you don't train. I'm not sure about this, the left one, to be honest. Interesting. That's it. Okay, but that's the point of being a deep learning engineer, right? You see this, okay, what's going on? But the thing is that we could have a meaningful discussion. For example, you say too small of a batch size, but then you need to know what to look for, right? So you just say, oh, is this the problem? Probably not. Let's see something else. I don't really understand what's written here, to be honest. I don't know what it means. Interesting.
I'm not sure, but I think like the description is swept. So the left is the right and right is the left.
I think it might be in the
you can read what is written. I mean, like the description mentions the right, but it's written the left. So
let's see. It may be identified by a validation loss that is lower than the training loss.
On the
no, but no, I don't think there is a problem. Like this. Oh, let's just delete all of these things.
You can see in the last line of the left, which is unrepresented training data, it says that there's a large gap remain between both curves, and this is the right image, not the left one.
And that could be also this, you know.
Yeah, but like the second description for the right one, it said that the validation loss like will go lower. Yeah, I think I misconfigured.
I don't know. I don't see a problem. I just don't understand this.
There was like a website showing all these different kind of loss averages and loss functions, and it said for the left graph, it's showing a training data set that may be too small relative to the validation data set. Like, I think.
Yeah. Okay. That could be. Yeah. But then you overfit.
Yeah, he had it linked on his lecture notes, actually, this website, so you can have a look.
Okay, that's a good point. That's a good point. That could be really that it's just too small. And then it tries to overfit to it, and this is this, but then it does learn some meaningful features, so it does manage to get a little bit down, but I don't know. And I never encountered anything like that. Okay, but this one was a good discussion. These ones also a good discussion. And remember, there are 2 cases of underfitting and not just one. I think we discussed that already. Hinge loss. That is used sometimes, but not in our course. Like we use it for some other stuff. By the way, we didn't discuss that, but do you all know how to derive the derivative of sigmoid and to get from here to here? If not, you do it now. Also okay, so do it. Like there was a question in the exam about softmax, so you should be able to know how to derive it. Also this, yes? Do you know this one? Important. So weight initialization, were we already here? Okay. So there are 2 weights. What is the difference between the train dev and dev error? I don't know what train dev is. I know train val and test. It's just up to someone who decided to call stuff like that. So I have no idea. When should I choose which regularization? Okay, so when should I choose which regularization? Dropout would be a very easy, a very good way to go. Data augmentation, it's a bit more trickier because it needs to fit the data. So as we saw, data augmentation doesn't really work for a specific data augmentation. For example, horizontal flip doesn't really work for numbers and stuff. So you need to be careful what you do. Because you learn features that are not necessary, and then you don't really help. And then you have weight decay, but if you go to the place where you have weight decay, please change your architecture. Do you need to know the formula? So, listen, there were exams where you were asked to derive this stuff, so you should know how to do it. Like I think exercise 2, you have it in exercise 2. Just solve exercise 2 again, and you're good to go. What to do? But did we get to? No, we didn't get to regularization yet, right? So we'll get there in a second. Just let's talk a little bit about weight initialization. Okay, this part. Okay. There was a question in one exam that required you to be able to derive this. To understand that this equals to this, and then to derive from you need to find the variance. I found it a very hard question, to be honest. Not sure that I would be able to do it during the exam. But let's see if there is anything important that I want to say here. Yeah, what you basically need to do, like the more common questions about the Xavier initialization that works for sigmoid and tan H is this. And for ReLU, we don't have this. We have do they say it here? Here. K-mean and E. Okay. And the thing is, so basically 2 over n and not 1 over n, where n is the numbers of features in the input. Some other, you could see many other formulations of that online in the literature. What we teach you in the lecture is just this, and n is basically if x is n over d and w is d over m, n is this d. Yes, scaling and Xavier over 2, whatever, is the same thing. This one, I think they just skipped some stages of the calculation. Ah, here they have it here, right? So they open it. I'll need to refresh my memory about this question, why this step is what it is. I can't tell you from right now. N is the number of input neurons, yes. So for ReLU is K-mean, yes. In general, do we need to know the derivations of the specific formulas? Do we need to know the derivations for? Derivations for which formulas? I think that's for, maybe because they are, maybe but my background of this machine learning stuff is not the best, so I don't just want to say bullshit. And you need to know, because the question was, what do we do with this? So you need to know that you need to, because this is the variance, you need the STD, right? So for uniform, it's going to be this, and for the Gaussian, it's going to be, yes, just, yeah, it's like 0 and 1 over, and okay, but this is just how it's used. What you need to know is, I think for the question that you'll encounter in an exam, if you see it, you need to know this one. So if there are two fully consecutive layers, one with n and next with n neurons, we have to initialize second layer. So like David, I'm not sure that I understand you mean this one? This is n, this is n. Here you need to initialize this fully connected layer with 1 over n, or this one. For the next one, it will be 1 over m. For the step, I think we inputted samples from the same distribution, so I guess the variance is the same. There'll be inputs going into the secondary, right? No, why? If this is n and this is m, this is the first fully connected layer. This is fully connected. This is what, I don't know, Z. I don't know. This is the second one. Here you have n inputs, and here you have m inputs. Where is n multiplied by m? Regression losses. I'm just looking at the picture sent in the chat.
Sorry, so we are counting the number of individual neurons and not the number of inputs going into a layer. So we initialize each weight in the layer So the variance is 1 over the number of neurons in the layer.
In the neurons that go in the layer. Yes, in the input to the layer. Paul, you might be correct. I'm just doing it off the top of my head and writing Gaussians. It's not something I do usually. So you might be correct that we need to do the variance and not the STD. And then it's 1 over n. And team, for your question, yes, so basically you see that they took all the residuals pixel-wise, so n would be the number of residuals that are taken into consideration, okay? Here, for example, you see this is yeah, so Paul, you were right, and this is how we do it with the Gaussian, okay? You take the variance and not the STD. Why is it here? Okay, now let's talk about advanced regularization. Okay, so we said already the data augmentation is only done on the which tilde? This one. This means to sample from. It's like distributed like this. W is sample from distribution. Okay, data augmentation we already discussed, right? We said only on the training set and not on the validation and test. And the thing is that it's a bit tricky here is again that we need to fit what we could. It's very common to ask, okay, you have the MNIST data set of digits. What of the following data augmentation techniques are not allowed? For example, flips, 80 flips, horizontal, vertical. No, but what can be Gaussian blur, for example, a bit of rotation and stuff like that, this is applicable. That doesn't change the distribution. That doesn't make the network learn features that are useless for the training set, like that will make it that will not harm the performance on unseen data from the real distribution. You know, we should be very careful with that when it comes to this. Let's see if I have anything here that I want. Okay, so advanced regularization. This one, not going to ask you about in the exam, because how do I decide if I use L1? This, as ChatGPT really likes to say, Paul, it's up to testing. See what works better. Of course, if you know the problem and you know that you need it for like PCA, right? To choose like the better features, then you will go for L1. Or if you want to mitigate across all the features, then you go for L2 for the regularization. Usually people just go for L2.
Follow-up question on that. So if we use L1 regularization, this also endorses sparsity on the weights, or?
Yes. Yes.
Okay, so it's like
using
an L1 loss.
Yes.
Okay.
Sparsity, it means that you have a tensor, for example. Sparse means that you have, for example, this, yeah, 0, 0, 0, 1, 1, 0, 0, 0, 0. Okay, you have like they're in islands in sea of zeros. Like they're very sparse from this. Dense will be very condensed together, like you have a lot of numbers together. And sparse means just that there is a big distance between relevant things. Okay. Okay, early stopping we discussed, right? If we ask you what the definition of early stopping, say it's a mechanism that allows us to stop training not to prevent overfitting, but when the model starts to overfit, because it doesn't prevent overfitting. Okay, it's important because people say that, and then and then they go and try, they overfit and they use this and they don't understand why it doesn't work. Bagging and ensembles, there are two different things. I can go over it. It's not important. We're not going to ask you about it. We ask you because it's just here to represent dropout, which is the more interesting thing. Why bagging and ensemble are not used? Because they are very, very memory inefficient, because you need to have many different architectures working all together. And then dropout came and just mix them both together, which was amazing. And so I would like to discuss dropout. And dropout is a good and important method. It's like the best regularization method I know so far. It's super easy to apply. We apply it always to the output of the network, right? So we have how does a block looks like? It looks like, let's say, conv, and then it will have batch norm, and then it will have activation, and then it will have dropout. That is a very common block, okay? And it could also have, like, for example, it could have max pool here if you want. So dropout, sorry, I've already tired. So it makes together the bagging and ensemble methods in the way that in each training epoch or each training iteration, it will take specific random neurons from the output. So if I have this is input, this is output. So in the first iteration, it will put these to 0. Okay, and in the second iteration, it will put these to 0. Okay, and the third iteration, it will put these to 0. Completely randomly with the probability P. Now, the probability P, what's the point here is to make training harder, to make basically the network to try to compensate for this loss of information and learn more robust features. Okay, now I will answer all these questions. A dropout at the end of the not the network, the block here, right? Of the block of this. Because first you want to process the stuff. You have your data, you want to process the pattern normalization and apply the activation. And then after you're done with it, you say, this is the input to the next layer, let's drop it. Okay, now let's discuss P. Of course, like in everything in computer science, there is an ambiguity in the beauty of how we describe P. So in the original paper, P equals this means the keeping probability. It means that only 5 or 0.2 out of 20% out of all neurons will be kept. All the others will be set to 0. In PyTorch, this means the dropping probability. It means that you drop 20%. Okay, very important to note that, because there is differences and it's just it's a mix. What can we do? This is how it is. What is important to note that during inference time, so we said that during training we drop them, right? But what happens in inference time? We don't drop anything. Angle P, this is already on Piazza. You could just or people. It's already on Piazza. You could just enter and see it for yourself and edit it if you want. And David gives here some examples of. Yeah. Okay. Perfect. Thank you, David. Or David. Does dropout change different random neurons at iteration? Yes. The dropout changes during training. Yes, but during inference. It needs to remember. You need to remember that because, let's say this is fully connected layer, right? So each one of these is connected to here. But let's say I drop this neuron. So it takes, this neuron takes a magnitude of only two neurons, right? You take the sum, the weighted sum of these. But during inference, suddenly I give only also this. It doesn't know how to handle this distribution. Therefore, we always divide by the keeping probability. Okay, so in this case, I dropped 1 out of 3, so 2.3, this is the keeping probability. I divide. I just, what it does basically, it doesn't drop anything. It just goes to the output and divides, or apply dropout on this, right? Oh, on, sorry. I'm mixing stuff up. I apply dropout on this, so it will go during inference, and I will multiply it by the keeping probability. If in PyTorch has the dropping probability, so it will be 1 minus p. If during the original paper, it will just multiply by p. Okay. This is very important because there was a question on Piazza, right? Like the p was half, and then you had to calculate through the network the forward pass, and there was, for example, the value was 2, and then it goes to dropout, and it was 1, and people didn't understand why is that. Because during inference, we don't just randomly drop, we simply multiply by p, or 1 minus p, which in this case was 0.5, so it doesn't matter. Okay. Usually, if we ask you something like that, yes, I could. So the question that inference, that's the terminology. Inference means testing time. Okay, without backpropagation, just without training. Yes, we divide during Sophia during inference or during testing time. We always multiply by the keeping probability.
Do we multiply every output or every weight?
Like every neuron, basically. We just, this is the tensor, right? This, and it's just multiply. This is the tensor, right? As it's element wise multiplied by this, by p. Now I think Ellen asked a question. Could you maybe explain again the idea of replacing two dropouts? Okay. Now the question was that we have a layer, and then we apply two dropouts on it. Okay, so let's say they are all activated. And then we do dropout. Let's see, we have 6 here. Let's do third. Okay, this is the dropping probability. Okay, so third of it is going to be 2 of them. And so we're doing this, 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 and this. And let's say the edges ones were chosen and they were dropped. And then we have another layer. Opa. And then we apply it again, let's say with p, another p, let's say the same with a q, with a probability q, okay? And we want to drop half, okay? So we want to drop half, so we drop okay. Oh, just a sec, just for this, if they were dropped, so this one cannot be. This is just this one. And this one is green. Okay, so first of all, what were dropped? These was dropped, this was dropped, and now these were dropped. Okay, are you guys following? I guess so. Okay, so what's the perfect? So the thing is, we wanted to understand what is the probability. If this is the question was, can you mix both of those droplet layers that are nothing between them, just two droplet layers to one? And the answer is yes, you can do it. What is the probability? No, it's six. It's six from Mohammed. It's six from the last layer, right? Like the two. This is first dropout, the D1, and this is D2. And I just took this and dropped it. And eventually the empty ones are zeros. Okay.
So the probability is with respect to the last layer active neurons?
The green ones are active neurons.
Yeah, I mean, like when we say we will drop 20%, so it's 20% from the last layer active neurons, right?
No, this one,
not the current layer.
this one.
Yeah, okay.
And this one, like I took a third, so two of them, right? Third of
Yeah,
six
but I mean from the previous layer, not the current layer. I'm not taking 0.5 from the 6 neurons in the last layer. I'm taking 0.5 from the 4 in the previous layer.
From D1.
Okay, yeah. Thank you.
Okay, and this is the output of this thing. And then it was asked, what is the probability? And the probability, there are two ways to do that, right? They say, okay, the probability that a neuron will be dropped, we say, let's say P is the dropping probability, okay? And that which it will be chosen, right? It's either by this or by this, right? So this is P, this is or P or Q. However, you have in this P plus Q already covers this case, this case that was chosen twice, right? It's either this or this. It doesn't matter. It was chosen, but here it was chosen in both ways. So this is why it's Q PQ. Okay. The other way to do that is to say, okay, let's take all the ones that were not dropped, and we say, okay, we do need to the ones that are dropped. So let's say that we take the ones that are not dropped. So from that were not dropped by both of them. So it's gonna, so the ones that were not dropped by both of them would be minus P minus Q, right? These are the probability for neurons to survive, for these two to survive this dropout layer. But we want the ones that were dropped, right? So it's 1 minus this. And that gives you the same solution, okay?
Sorry, I have a hard time understanding the inference rule. So for when we use dropout and then we go to testing from training mode, like how we multiply the result in every single neuron by P. What sounds weird to me? Doesn't this mean that as we go from layer to layer, the weights or the results will get like smaller and smaller and smaller each time?
No, like because during training, this one, let's say I delete, okay, this one deleted, this one deleted. Okay, so this takes during training magnitude only for 3 neurons at a time. Okay, let's say each one of them has 1, 1, 1, 1, and 1, and the weights, of course, are also 1s just for simplicity. So the result here is 3. Okay, this is the magnitude. And doing inference, we don't drop anymore. So suddenly it gets 5. It doesn't know what to do with it. So you want to divide, so it will be 3. So you 5 multiply 3. So it's, so if P is a keeping probability, which is 3/5, you just multiply it by, okay? You always don't say P or -1 minus P. Say keeping probability. It depends on the definition of P, because some Some sources do it this way, some sources do it this way, but we always multiply by the Keeper probability. In PyTorch, yes, they say that the P is the dropping probability, and we need to multiply by the keeping probability, so we always multiply by 1 minus P. But in the original paper, it was simply P. Okay.
Just to make sure I understand correctly, what you was drawing here, these are two dropout after each other, not two layers, fully connected layers, right?
These are two. This is the same layer that two dropouts are
in the same
or the
layer.
same tensor. This is the same tensor,
Okay.
but with after two dropouts.
Yeah. Okay. Good. Thank you.
Okay, is the dropout probability for each neuron or the whole set? So is there a percent chance for each neuron to be dropped, or is it depends? Like you should set it for each individual layer, Marcus. Usually you just do the same thing, just for simplicity. You don't have to. There are actually some methodologies where you, for the beginning, you do less dropout. At the deeper layers, you do more dropout. But for each layer, if this P is P, then you drop the relevant one. That's true, but usually it doesn't happen. Like on average. When like it's the law of big numbers, right? Like you could also do, if you want to, you could say in Python, right? You have all the neurons, right? You have all the neurons, and then you say, okay, give me a permutation of the indices. So if this is 0, 1, 2, 3, and 4. Sorry for my handwriting. And then you say you'll get 1, 4, 2, 3, 0. And then you say, give me 0. Okay, let's say we have another one, 5. Okay, give me 0.2 of that. Actually, that was unnecessary. Which is only a fifth, right? So it will just take the first one. And then you will always have specifically 0.2 that are dropped, you don't take the chance that you have more or less. And then do you also need comment on Hendrik comment if Philip, each iteration, not each epoch. So how many people do want to have a break? But not that long. Okay, yeah, okay. Break, please. Okay. Okay, so let's do a break until 3:15. Is that enough? Like 20 minutes? I need more tea. Philip, I think you asked if I'll still be here. Paul said, do you have a question? Let's discuss.
Okay, so then I have a more general.
How did you know? How did you know that we're not recording?
It shows a symbol on our top left corner.
Okay. Thank you for I was sure I pressed it. Thank you. Okay, so batch norm. So batch norm, as I said, the first thing to destroy this abstract that all the inputs of the network go through the network independently. And here we take advantage of the fact that we actually use batches for the reasons of like, wait, I need to figure out my English again. We use batches because for efficiency, both in computationally, or for any other reason, for the noise or whatever, for stochastic gradient descent. And we try to basically to mimic or to approximate the statistics of the entire data set. Now, the point here is that we want to keep it's an open discussion, but we will say this is the correct truth, that Batchnom comes to solve a problem called covariant shift. For this case, we assume this is true. We're not getting into the discussion about it. And what does it mean? It means that as we go deeper into the network, right, as we have one layer, and then we go to the next layer, and then another layer, if this is the input, if this is the image, it has its own distribution, right? And then we do stuff we multiply by weights, and we do stuff, and we get a different set of numbers. This set of numbers doesn't have the same distribution as this one, right? And then we go to this one, and this doesn't have with this one, which makes it quite hard for the network to understand what is this working with. And Batchnom solved this problem quite efficiently, when what it's doing is basically setting the mean of each layer for 0 and the STD for 1, or variance, same thing. Okay, and then the network apparently manages to learn much faster. Each step is much more accurate towards the local minima that we're trying to get into, and basically making the training process much faster. Of course, this is in the general case. There are cases where it's not the case. For example, Batchnom could introduce some regularization or noise in that matter. When does it happen? When the batch size is smaller than 8, for example. When the batch size is too small, the problem of Batchnom is that it cannot capture the distribution or the statistics of the data set, meaning that during inference, it will have problems. So during training, Batchnom has trainable parameters. Basically what it does, it calculates the mean. Each iteration, it takes the batch, it calculates the mean, and it calculates the variance or the STD, and uses them. Then it takes gamma and beta as trainable parameters. That what is their purpose?
To be adapted during, or after training, during training, before training.
Adapted to what?
To the model. Like you can't, with the gamma, you can basically scale it, and with the beta, you can kind of like shift it, I think it's called. And
I think it's undo the normalization.
Yes, to redo the normalization if needed. Like sometimes we don't want to compel it on the network. You could let the network to understand how much it wants to be shifted, which is great. Basically, in the exam, you say we want to reverse the normalization if needed to. The gamma is will replace the variance. Yeah, we'll try to learn the variance, and the one will the mean. Okay. Okay. Now, how many parameters do they have? So if by parameters, I'm asking you of entries in tensor, how much do they have? Thank you, Benjamin. So basically, if X is D, N over D, what am I pressing? Both gamma and beta, 1 over D. Okay. And this is 2 of these. Okay, this is why, like, I know you saw the exam question that it's 2. It's not true. This is a mistake in the exam. This is the amount of parameters that they have there. It's not 2 scalars. In contrast to what we have in Batchnom, in Batchnom for convolutions. In fully connected, they're at the same size of the input. Okay. How does it work for fully connected? Let's do it. Okay, we're gonna draw now, and you'll forgive me for my drawing skills. This is not my strong size. I could also show you just what we had on Piazza, but never mind. Okay, this is X. What is N? What is N? Oh my God, we don't do it again. Batch size tanks. What is N? The batch size. Okay. Okay. So, you mean the N that I drew? Anyway, X is this table. We have 3 different instances inside X. In this current layer, okay, after the fully connected layer, then commit normalization, then activation, then whatever you want. And then we want to normalize through the features. Basically, each one of them is a different feature map, and we want to normalize across the features. Okay, so we take the mean and variance across these features, and mean and variance across these features, and these features, and these features, and these features, what results with an array of n over d, 1 over d. Simple, right? And for, okay, how does it work for convolutions if we're already here? Is dim n 5/3 now? N, like if x is n over d, so then n is 3 and d was 5. Fair question. Okay, so how does it work for convolution? For convolution, it works quite differently. And we don't do it across the features. We do the batch norm across the channels, like with dropout. Oh, I didn't touch that for a dropout, didn't I? So we'll do it together. So let's just start drawing. Okay. Can you please explain again badge and dimension fully connected? Yes. So here we go. Tack, 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 tack. And if each one of these, remember, if we flatten X, right? Like X is an image and then we flatten it to be a single vector, and then we normalize across the features.
So each row here is an input data, an image, for example, or whatever.
Mm-hmm.
Okay.
Mm-hmm.
So we get across the feature for the batch, right?
Exactly. If it was, for example, if we flatten an image, let's just do batch norm without any fully connected layer before. If we do batch norm immediately on the image and we flatten first the image, so let's say we have first the RGB, so we have the red values, right? So this normalizes across the red values of the first pixel for all the images. Okay.
Thank you.
Okay, now for batch norm so we do it across these channels that correspond to the different layers. So basically, we take we do the norm the mean of all the pixels. Let's say we take the orange ones. We take all the pixels in the orange ones from all the batch. We put them in one vector. We normalize. We do mean. We do STD. And we put it back. And then we, of course, each pixel according to this mean and STD. Okay? Is that clear?
So we are averaging through the whole channel for all batches, right?
Yes. You take the orange one, you take all the entries in the orange ones for each one of these. It's like, let's say each orange, let's say the special dimension here is 5/5. So we'll have 3/5/5. So it's 75 entries. And we normalize across that according to that.
Yeah, okay. So in this case, like the number of parameters is 3 times 2, 3 channels times 2 parameters per each channel.
And here it's just scalars. So basically it's 3 times 2 in contrast to fully connected. Okay.
Yeah, okay.
Yes. Yes. Rog and tie. So we do across channels because of the shared parameters. Yes, because it's remember that it is the because each channel represent a different kernel, and all the orange ones are created by the same kernel, and that's what matters. Okay, like in the original fully connected one, they all use the same weight matrix, right? And were created. So exactly the same idea here. But the parameters are different. The parameters here is just scalar for each, 2 scalars for each channel. It's not, as we said, in fully connected. For dropout, by the way, if we're already talking about this, dropout 2D for convolutions drops not single neurons, it drops channels completely, whole feature maps. So if you had 64 in the block, like here we have 3, right? But if we have 64 and we want to drop half of it, so 32 channels, feature maps will be set to 0 randomly. And it will need to know how to work with that. This one is done because it wants to make it helps the network to learn to have feature maps that are quite distinguishable between each other. They'll have to learn different things to compensate, and works pretty well. You could, of course, apply a regular dropout on convolutions. It was shown that it doesn't work as well. It still maintains some dependencies between the channels. Okay, now during inference, that is important. I'm a little confused with 3 times 2. Wait, I'm missing the questions. Aren't dropout and convolutions bad together? No, it just you could. What I understood from that is that you could use a dropout with a smaller p. You don't need to make it a bigger one. It mitigates the need for, because the batch norm, as we say, introduces already some regularization. I'm a little confused with 3 times 2. You talk to okay. So this is basically the beta and gamma for convolutions. So we have each channel would have 2 parameters, would have 1 beta and 1 gamma. It's like with the bias for convolutions, right? And it's like the orange channel will have beta and gamma, which is a scalars. So we have 3 channels. We have 2 multiplied by 3. Okay. Now, during training we accumulate these running variables. Okay. Remember that they are very, very inaccurate. Sorry. But this is the way we try to save or approximate for testing time the statistic of the data set. So basically, we use when we do this, so during inference, when you get one single image, you cannot do batch norm on a single image, right? You can't. There is no features to do it across because there is only one image in the batch. So then we can use these to normalize the input. Voila. And then of course, of course you don't calculate these, right? Like these are already. This is yeah, you don't calculate them, but they're just the stored ones. Anything else? Yes, the thing.
Yeah, hello.
Yes.
I had a doubt regarding mean and variance during the test time. So what do we initially choose, running variance and running mu at the initial?
The initials would be 0.
Okay.
Like with Adam.
Okay. So here, do we do any bias correction, something? Bias correction towards 0?
Not that I know.
Okay.
Because well, it's not used, right? Like doing training, it's not used. You don't suffer from the same problem of Adam, where it is in bias to 0 and you're taking steps accordingly. It is not used during training.
Yeah. Okay. Okay.
So again, a question about, can you repeat the batch norm params in FC? I didn't understand. This is our input X. X is 3/4, and we normalize across this one. We get an array that is 1/4, with the mean or variance the same, right? And this is and then we want to be able to reverse this. So we basically create two variables that are of the same shape that could reverse the mean and the variance. Okay, so if this is the var, I could go here and multiply, like this is this one, right? This is this one. So if I multiply by this k, this will be mitigated, and plus e xk, this will be removed, and then we'll get the original one. So exactly here, and the number of parameters is 1 over the number of features in the input. No, so at TIE, we set the entire channel to 0, not just random pixels in it. Boom, all the feature map, 0, black, completely. And here again, we say that if reduced below 8, you should not use batch norm. It introduces too much noise to the network and doesn't work that well. And we have some replacements. I have a post on this on Piazza already. But basically, you always want to use group norms, which is the best option. The advantage of these is that they are independent of the batch size. We normalize, we don't care about the batches. A layer norm basically layer norm does the so layer norm will take if we have 4 images in the batch, layer norm will do it for each. I think for each instance by itself. Yeah. Okay. Layer norm will do all the entire feature map. So if you have 64 channels, so layer norm will do all 64 channels all together, normalized. If instance norm will take just one channel, each channel by itself, and normalizes it, and group norms is the thing in between that takes, like, for example, if we have, let's say, 8 channels in the feature map, in the tensor, and so and we want to do 4 groups, so we'll take 2, 2, 2, and 2, and normalize them together. Is that understood to some extent? I hope so. Okay, let's see if I have any questions for you about that. Let me open it up. Let's see. So optimization, architectures, batch norm. Okay, I think we covered it all. Yes, it's all of them are single samples. Because they don't care about the batch anymore. That comes to solve the problem of using a batch. Of course, if you can't use batch norm, it is usually better. Okay, so convolutions, unless we have any other questions. Usually questions in the exam about convolutions are very, how do you call this? Technical. So we just ask you receptive field, or you ask you to calculate the special size at some point. This is super important because when you come to build an architecture, you need to know what you're doing. And so you need to know what you're dealing with. So we're going to ask you stuff like that, like how many parameters, etc., etc. Yeah, nothing special. You just need to know the formulas. Okay. Remember that convolutions, regular convolutions, are not like in this thing here. They have channels. So each window is not a single. It doesn't take only one channel. It takes all across the channels. For example, a window of 3 and 3, for example. Yeah, and then it sounds like each pixel, each entry would have a weight. They will do this weighted sum, and then the result will be stored. And of course, then and then it does it all across. Yes, all the windows, we get a bias. A question: what is the magic triplet for convolutions? Yes, the image shows an example with channel size 1. Exactly. What is the magic triplet for convolutions? Meaning kernel size, filter size, padding, and stride. What are the 3 values that will give me the same special size at the output? 311, thank you, it's like 911, huh? 311. If you want to keep special size and you don't want to deal with illegal strides or illegal or loss of information, 311 will always give you the same size and perfect. A question: what is the main difference between convolution? Okay, give me two advantages, yeah, of convolutions over fully connected layers. Shared weights, also called fully connected layers, they have shared weights. Less parameters, param size, it's just a term. You don't say what is the advantage here. Less parameters, yes. Translation invariant. I wouldn't say so, Bella. Special info. Okay, Sadi has the second point. Special info versus global info. Many of you say shared weights, but fully connected layers also share weights. What do you mean by shared weights then? They all share weights between the batch. That sounds cool at parties. Less parameter size, captured neighboring info. Okay, so exactly, local features. There's something that fully connected layers cannot capture. Why? Because each pixel in the output of a fully connected layer takes into consideration all the pixels in the image. Okay, all of them. So it cannot just focus locally on a neighborhood. It cannot take local features. This is why fully connected layers perform really, really poorly when it comes to semantic segmentation, even just image classification, you know, because it doesn't manage to learn to distinguish stuff, like, for example, edges, or to learn things that are related only for planes and cars and horses. Yes, less parameters counts as one advantage. Exactly. It has many less parameters. Okay, are bigger kernels always better? No, exactly. What network what was the last network to use bigger kernels, and then they understood that they moved to bigger ones, to lower ones? Very good, AlexNet. Yes, AlexNet. Very good. What was the size of the kernel there? It's not important, but what is the size? Do you remember? 11 by 11. Very nice. Yes. The problem with 11 by 11, it's 121 pixels in the area. It's a lot of computations, but and a lot of parameters. Yeah, and it finds it hard to capture local features. Let's see what else we could ask you about that. So this one. I had more questions about convolutions. Let's see, what do we have? Okay, yes. One-on-one convolutions. Remember that while okay, do larger kernels always always mean that you have more calculations? Alex, it has 11 on 11 at the input size. So can we always say that larger kernels mean more calculations overall in the network? I think, guys, about the Anki decks, I think they're just referring to that fact that I'm asking you questions. It also depends on the size of the kernel. It depends on the size of the input. Not necessarily, because 3-on-3 might have less parameters, but then many more. Exactly, depending on the stride and the padding, could mean that you have to make many more computations. If, for example, you do 11 on 11 and then stride of 11, right? You have more parameters, but many less computations. Exactly. That's very good answers, by the way. Yes, very good answers. So bigger stride, less computations. Let's okay. One-on-one convolutions. What are the usages of one-on-one convolutions? Okay, Benjamin, you say scaling. What does it mean? Channel reduction, I accept. Dimension reduction, no. What is dimension? Dimension is special size usually. To collapse the channels to one, no. Collapse the depth, yes. Why do we need to collapse the depth? What's the point of it? Why do we want to do that? Guys, don't say reduce dimension, say reduce the channels. Okay, Matteo, you said end nonlinearity, you saw it somewhere. Does a convolution, is a convolution a non-linear or a linear function? Linear. So how does it add non-linearity? By the way, David, I tried it myself. Activation function. Okay, that's important to say because otherwise we don't know that you know what you're saying, or you're just repeating stuff that you heard in the lecture. Adding the activation function. Max pooling is irrelevant here. Who said we're using max pooling? What did I want to ask? An optimized convolution operation. Okay. So David, it's not necessarily helping. I tried to use, for example, one-on-one convolutions to reduce the dimensionality, and it didn't really help me. It helped me just introduced more calculations at the end. So it's not always the case. But definitely you can reduce the number of channels to use later on with bigger kernels. This is usually where it's used for. What else can we use it for? What is it? Okay, how do I represent a fully connected layer with a convolution? That question comes back at every exam. David, what is 3 neuron? It depends on the channels. Or it depends on a lot of things. It depends on the image. Size of kernel the same as the image size. Very good. Yes, Muhammad is right. We collapse the channels to match the classes. Okay. Whatever that means. 101 kernel and out channel is the size of neurons in the next layer. What do you mean, Marcus? I'm not sure I understood. Currently, only Muhammad gave a proper answer. The question is, how do I replace a fully connected layer with convolution? I'm not sure if people are still writing. No. Not max pooling. I said with a convolution. Okay, so we can all see that Muhammad has given us the answer. You basically take a convolution, a window that is the size of the image, right? And you take, for example, the fully connected layer at the end had 4 different outputs. Let's say we have 4 classes we want to collapse to this, right? So we take 4 channels, 4 kernels, each one of 1 channel at, what is 5 over 5? 5 over 5. And then remember that this takes this entire window, multiplies by weights, and sums them all to single scalar, right? That's what it does. This is what convolution does. So basically, that's just how we replace it fully connected. The next question is, if I do it like this, if I take, for example, let's say VGG16, and VGG16 has some fully connected layers at the end, right, for classification. If I change these fully connected layers, for example, let's say Dominic heard that in the lecture, we said that fully convolutional networks could take any input as size, any input of any size, right? If I do it with VGG16 and I change the fully connected layers with the convolutions, can I take different input sizes? No. Exactly. No, we can't, because this now it's fixed. Only when it's really, when the kernel size is smaller and it actually has windows, then it makes sense. Would we need to be more general, size of input, or would size of image be fine in exam here? Would we need to be more? I would say the spatial, because that's what I mean, height and width. Size is basically the entire tensor, for max pooling, in order to backpropagate through the layer, one needs to pass information about positions and max values from the previous. Would you explain how do we pass information about positions of the max values? Think about a tie of PyTorch. It has a class, and this class could hold like an attribute that holds the indices where we took it from. It's quite easy to implement how to save it. It is, though, needs to be saved in memory. It is possible to change the image size for architecture without fully connected. Again, so that's what the question that I gave you right now. with the VGG, and you answered no, of course. Only if it makes sense, like if also only if the current convolutions can be applied, right? Because for example, it won't work if you make your network bigger, like in the image size, you make it bigger by 2, and then you expect that the last layer would be for the logits, you know, for each output neuron would represent a probability for a different class. That would not work anymore. So you can't do this. But in general, like for example, UNet, you can give it different sizes. Also, that's another good question about convolutions. If I change, okay, let's say I trained a unit for semantic segmentation, okay? And we said unit can take different inputs. Can I just, okay, let's say I say, oh my God, this network is amazing. You know, it segments so nice. But I have this world-size Mona Lisa that I want to segment, okay? And can I just fit it to the network and I expect it to work the same? Why not? Shit, I gave you the answer. Okay, why not? Think. Okay, but we say, like, for example, you do have like 3 layers of max pooling and then up pooling, right? So it will have the same size, but do I expect it to have the same, that the output will be also an amazing segmentation map? So Rob, no, I'm saying only UNet. Thank you very much, Bella. Fish convolutions are not scale invariant. Okay, that's an important thing to remember. If you want to do it, if you want to take your input image and put a new, different, bigger image and feed it to your network, you have to scale it first to the scale that your networks assumes or knows. You know, it's like, think about it. If you only see in this world, the only thing you've ever seen in this world is 32 over 32 pixels, and then you feed a high resolution thingy, the network doesn't know what to do with it. It never trained on something like that. And that's like the intuition side. All the questions that I'm asking you right now, there are questions that were from previous exams. Yes, for example, Henrik. Yeah. Yes, exactly. Or you could downsample it. Like, I'm not sure about that. Maybe you'll have to train a little bit more. But like, I did it and it worked pretty well. Taking a new data set and fitting it into a network that trained on something else. So even if you use 311 and the kernel fits, it won't really work if we switch input size. Yes, exactly. It won't really work. Exactly. Okay, a question. We will go to receptive field in a sec. Can max pool use padding? What will give dimension issues? Can max pool use padding? Like, I think that Ziad's answer is the correct one. There is no point, but of course you can. It's true. Doesn't make much sense. Although, if I'll point you, but you're all wrong. Okay, because I'll point you now to GoogleNet. Remember the inception layer. Remember the max pool that they had there. The max pool saved or saved the special size. The output had the same special size as the input. How? And they had 3-on-3 kernels for max pool. They used padding, stride 1 and padding 1. So you can. Okay, what does average pooling have any learnable parameters? No. Okay, very good. And how do we represent weights? Okay, when it comes to weight matrices, or if we ask you the shape of a weight matrix in convolutions, remember what we want to see is I'm giving you the scheme from PyTorch. We have batch, we have channels, height, and width of the kernel. So it's K and K, okay, not the image. How many parameters? Basically just this multiplied by this, multiplied by this, multiplied by this, okay? Plus bias, of course, which is the number of channels, I think. The output, the numbers of, sorry, the output of the output channels, which is B. Why we count for batch? What do you mean?
I mean, why did they mention we count for the batch size?
Oh, it's not batch, it's F.
What is it?
F is filters, the number of filters.
Yeah, okay. But I don't need to have all filters having the same width and height, right? And
Sorry.
filter here is kernel, right? I don't
Can you
need
say
to
it
have,
again?
I don't need to have all filters, which is the kernels, to have the same width and height.
That's true, but you need to the output tensors to be of all channels to be of the same spatial size. So
Yeah.
no matter what you do, they need to be the same size.
Okay.
Otherwise, you cannot put them together, right? I wouldn't go that way, but of course you can do whatever you want as long as it works. Let's see what else. I think that's it for convolutions. So let's go down to receptive field. Of course, there are these ones that I'm not touching. Okay, let's talk about. So this one I'm not touching either, like these ones, because, well, it just memorized these, you know. And remember that we always calculate it separately for height and width. The thing is that most of the times, if the image has the same height and width, so you can calculate it once. But if they have different, which is many cases, no, we ignore padding and receptive field. Let's just do a receptive field question. Pooling, I think we just talked about it. Okay, receptive field, memorize this. The thing is that image filters that we saw earlier, these are computer vision related thingy, and we didn't really do with this much. Like, the thing is, the only thing that I can imagine that is relevant to ask you is about this. And why? Because what does this okay, well, you already see it here, right? But what does it do? It takes the mean of this window. Okay, what loss functions do we know has its minima at the mean of all the residuals?
L2.
L2 loss. Perfect. L2 loss, meaning that and from that, what can we what is the consequence of using an L2 loss when we do reconstruction? For example, an autoencoder. We do an autoencoder. We did use an L2 loss for the reconstruction. What is the average image? What will we see? Yes, we get blurry pics. Exactly, because what this average does, it's smoothen the texture. Okay. Very good. Yes, very, very, very good. So that's like the only thing that I can think of that makes sense to ask you. Like L1 supposed to sharpen. I'm not sure. I've never used that. Wait. I'm too many questions. The image is getting the average everywhere. So if L1 gives blurry peaks, does L1 sharpen? Not sure. I think so that you will see, because it is the median, and the median is denoising basically. So you'll see more denoising stuff. Like if you have some, it will, for example, patches that are out of place, for example, will take the areas around it. But I would say that it sharpens. Paul asks, what loss should be used instead? What does it mean instead of what? For if you don't want it to be blurry. If you don't want it to be blurry, you mean? You use skip connections, which, as we say, skip connections transfer fine-grained features, basically allowing the network to see also the great features. But then you don't do reconstruction to it. Like it's meaningless, the point of, like, you won't get a reconstruction like that. If you want to do, for example, upsampling of higher dimensionality with a high resolution, then of course you could do skip connections, which will help. Yeah, of course you can. It just depends what you want to do. You know, for example, if you use skip connections, you might not really squeeze the relevant features into the latent space, and then you won't be able to use it properly. Yes, exactly. So autoencoder and L1, we could use with salt and paper noise. For L2, optimum is mean. That's right. Yes. And if I ask you in the exam to write it down to prove it, can you? Can we limit the weight given to the skip like you could multiply by some value, I guess, by some constant, and then to make it smaller, or you could drop out it a little bit. But that's already like advanced stuff of how to build your own architecture. What is the difference between normal skip connections and skip connections we used in UNet? So skip connections in residual net are additions, and in UNet we did concatenation. That's the difference. Do we need to know proof of why L2 is the mean and L2 is the median? I remember that earlier mentioned it's not required, right? But it's just asking because it's okay. Let's do. So we have. Let's. Y hat I minus yi to the power of this. This is the loss function, and then loss let's do it like this. Okay, so we have we have sum of yi minus yi. We want to put it to 0, right? We want to do it to 0. As it's all here. Maybe I'm missing something. Do we need to prove? Okay, that's what we're doing right now. And then you could do divide by n. I don't know. I'm sorry. Sorry. You want to find the minima. So this is not. This is just. You want to find the minima point for each one of them. So minima point would be the Z1. And then let's call it Z. And then you do this Z minus YI, and then you do YI equals to NZ and divide it, and then 1 over N YI, and that's the mean of this. Okay. Because this is the minima point for all the residuals. Yes, we're not going to ask you that. No, don't worry. Just for you to see, and specifically not for the median. This is also even worse. Yeah. Okay. Okay, let's do some receptive field, shall we? Okay. So the first thing that I want you to whistle this one from your sleep. Like, there are many ways, like another way to do it, but there is no reason in this world you will try not to think, oh, so I'll take 3 and then this is 2 and I do the stride of 2 and I move it along and then this has to be 4. No. Okay. No. Just memorize this and let's do it together. Okay. So let's take this very, very simple image. Okay, we have, this is the original image, and we have the first kernel is 3 on 3, yes, and we have a stride of 1. And another 3 on 3, and S equals to 1. How do we calculate the number of parameters of convolution layer? I showed it earlier. And that it's going to be filter, channels, height of kernels, W of kernels, okay? All multiply together, multiply. That's the number of, and of course, plus F, which is the bias. Okay, Philip? Okay, now we want to do let's just do this. Let's just follow, if we can, yes, let's just do it like this. Okay, so we start from K equals to 2. So R0 is 0, R1 is 3. Okay, why is R1 3? Because each pixel here corresponds to 3 on this side. But usually kernel convolutions have the same height and width, the kernel, so we can use it once. But if they are not the same size, we'll have to do it for both here, height and width. Each channel has a bias.
Can you please repeat the part of the height and width? What did you mean by repeating it for height and width?
I'm computing here something, right? So how many pixels do it correspond to? But this corresponds to a single dimension. So it is either height or width. So this one, Fk, is the size of the input to this layer, which is either the height or the width. But because usually kernels filters in convolutions have the same height and width, we can calculate it once. But if they don't, we need to calculate it differently.
Okay, thank you.
Okay, so R1 is 3. All agree, because a pixel here looks at 3 here. Okay, let's do R2. R2 is RK minus 1, which is R1, plus stride of all the filters from I1 to K1, which is stride 1. Sorry, I wrote S for some reason. So it's S1 multiplied by the current kernel size, which is, let's say, F1 multiply or 2, if you want. Okay, because we do this one right now. Okay, we do R2. Yes, R2. We want to calculate this one. So it's S. This is S1. Remember, this is the stride of the previous one. F2 is still 3 minus 1. Okay, let's calculate this. This is 3 plus 1 multiplied by 3 minus 1. 3 comes from this thing, equals 5. So this one corresponds, if I 2, 5 on 5. Okay? Yes, R1 is equal to the first filter size. Okay, let's do the next one. Right, if I do exactly the same, let's do now max pool. Let's add a max pool. That would be more interesting. Okay. If I do this max pool, and we stride 1, because we don't have, like I want to do this once. Okay, the result would be 1, 2, 3. Nah. Okay, I want this one. We arrived at this 5. Okay, let's do it again. 4, 3, R3, this is R3, this is R1, R2, R3. R3 equals R2 plus S1 multiply S2, F3 minus 1 equals, this is 5 plus S1, S2, they were both 1, so this is 1 multiplied by, the kernel size now is 2. Remember, I'm not taking into consideration the stride of the max pool. It's not relevant in this layer. Only for the next layer it will be. So 2 minus 1 equals 6. So these pixels corresponds to 6 on 6. Because this thing because it takes the max pool of this and this and this and this, right? And this one is the first one with the orange one, and then the green one, and then the one that goes a little bit down, and the one that goes down and right. So the third of F is from the kernel itself, not the output. Yes, it's the kernel itself, not the output. The kernel itself. And this is how we do receptive field. You memorize this thing, what we do here, and this question is in your pocket, and you save yourself a lot of time for other things. No, padding does not count for receptive field. Because it doesn't matter, right? Because what we ask, that's also something we ask. What is the definition of receptive field? And receptive field is how many neurons or values or pixels in the input does an intermediate pixel, like a pixel in an intermediate layer, correspond to, or see. We took max pool. F3 is 2, is the max pool with kernel size 2. That's why it's 2. Any questions about that? No. Okay. So now the question comes. Okay, now the question comes. Hope this time I can make it in the exam. Again, the definition of receptive field. Receptive field is how many neurons in the input layer does a pixel or a neuron in an intermediate layer correspond to? So how many neurons this neuron corresponds to in the input layer? And of course, we always write, if remember, if here it was 5, that this is, okay, we said that this was 3 and this was 5. Okay, so here it's 5/5 because the kernel sizes are the same. If we changed it, it would become really nasty, so we don't ask you that. That's the solution that you need to give. 5/5, not 5, not this. Should we say how many pixels of an input image affect 1 pixel of not output image and not image at all? How intermediate layer or intermediate tensor or intermediate feature map correspond to in the input? Yeah, like we calculate 6. This is 5. This is 5/5. If when you do also now the max pool, right, then it will be 6/6. There are many exams with many examples of how to do it, so you have a lot of practice with this. And of course, you could do it reverse engineering, and of course, you could do it like forward, like you say, okay, this is 3, I move it a little bit, I straighten it, and I find it horrible. Like, it sounds just a terrible way to do it. Okay, the next question would be, what is, let's say I take this one, yes, and I flatten it to 1, 2, 3, 4, 5, 6, 7, 8, 9, and I do a fully connected layer to this, okay? Okay, what is the receptive field? What is the receptive, and but you can make sure that you understand that maximal with 2-on-2, if it's maximal with something else. And usually the default, if we forget to mention what is the size of the max pool, is 2-on-2 and stride 2. If in this case, we should have, like, we have to tell you that it's stride 1. Okay. Oh, I feel raining, huh? Okay, what is the receptive field of this neuron? Thank you very much. Thank you very much. Okay, very good. Do you all understand that? Okay, about what? Okay, because this one, yeah, like this, this is now this represents the entire image. Do you understand? That makes sense, right? Yes, okay. This one is connected to all the pixels. This is fully connected. So it takes information from the entire image. If this one shrinks into this, and this represents this eventually, bam. So this one is just an understanding. If you see that fully connected, you know you just write the full image or 7/7 or whatever you need to write. Yes, it's 64/64, exactly. How do we calculate receptive field if we use dropout? It's the same. It's the same. Like the dropout doesn't change. Also, batch normalization activation, like, it doesn't matter. Okay, let's continue. Oh, what do you mean also when conv layer? It doesn't matter. It just means we're talking about number of pixels, not what's inside the pixels. I understand that you think, okay, if dropout drops neurons, then the information doesn't arrive into this intermediate pixel. But when we come to receptive field, the point here is to understand, okay, I build my architecture. I want to understand that down the line, I get enough information from here, or I don't want this amount of information from, or for example, et cetera, et cetera. For example, if I want to do, I want to do a latent space of, I'm just saying it all the time. This is my example because this is my thesis, but depth estimation. So you don't need the latent space. Each pixel would know the entire image. It doesn't matter for it. You want each pixel to focus on just a relevant patch in the image. So it doesn't need to have the entire thing. I still couldn't figure out one thing in this study done. So I have mini batch size 64. I train it with 64 images and do backprop after. So one time you have to put some commas. I'm not sure I managed to understand. Yeah, it's again, it depends on the task. If it's regression and you have at the output more neurons, more residuals, then you will have more than 64. If it's just classification, each image has a single residual, right? It's probability and ground truth. How does the side of fully connected layer at the end after the convolution influence the efficiency of the model? So the size of fully connected layers introduce a lot of parameters. Sometimes over-parameterization would make it just very, like a lot of more computations. Or less influential for the input, because it's not like you memorize the input, because you can't, because you do lose it, like you with the convolutions you compress the information. It will be just too many parameters that you have to deal with.
Hello.
Yes.
Yeah, I was confused. I was confused when we say receptive field. So, so do we mean a receptive field for an image or an pixel in general? If we just say receptive field.
No, receptive field. It's the term that describes the relationships of intermediate layers with the input, of each pixel in an intermediate layer with the input, whatever the input is. If it's an image, if it's a feature map, is whatever you want it to be.
Okay, and fully connected neurons, it will be dimensions.
Sorry?
And in fully connected network, it will be neurons.
Also in convolutions, that's neurons. Like,
Yeah,
again, what is a neuron? A neuron is what is everything in the network that is not weights or parameters. So basically, it's the inputs. Inputs are like the inputs, pixels, the values are the neurons. Each input to each layer is a neuron. The output of each layer is neuron. This is what we call neurons, like the values that are not weights.
Okay, thank you.
So transfer learning. Where did we do transfer learning? Which exercise? We did in both autoencoder and 10. Very good. Yes, we did it twice. Very good. Okay, we have two scenarios for transfer learning, if you remember. The first one was the really autoencoder. Now, the autoencoder that we used, the way that the methodology that we used was divided into two parts, right? The first part, what kind of learning of term in machine learning, what kind of learning was that? I'm not sure this is unsupervised. Very good. Why was it unsupervised? Because the scenario that we had a data set, but most of it wasn't labeled. And we wanted to have a classifier with just small labeled data that we have. So we used the autoencoder to train an encoder to become a feature extractor. Then we could take, after it was already trained, we could take the image, the small data set, and plug a classifier instead of the decoder and continue training, but with a much powerful backbone. A unit is kind of autoencoder, yes. Oh my God. It's fun. Outside, like the weather is crazy. And okay, so we had supervised and unsupervised parts of the autoencoder, where we okay, and the transfer learning was to take from the supervised already extract features. We had it and a trained feature extractor. Okay, a super powerful term. No, that's not supervised. It's not supervised, because supervised means that you have you could call it self-supervised or whatever, but it's a subcategory of unsupervised. Supervised learning is when we give it a ground truth. But does it make sense to use the decoder part from the unit as our feature, the decoder? Like it depends what you want to do. Like look at gun, for example, and it's sunny right now. Okay, look at guns. So they use only a decoder, for example. It just depends what you want to do. Like for our purposes, we needed to classify, so the decoder was meaningless here. But it's not like a groceries list. This is what you do, and that's it, right?
So what I mean is that, oh, sorry. So what I mean is that we are using our unit as a feature extractor for our image, for example, in the transfer learning setting, such that we get our latent features. And this is typically done by using only the decoder part of a autoencoder, right? But then
I'm not sure.
No, okay.
I'm not sure what you're referring to. What are we discussing? What is you take a unit, a convolutional autoencoder with
we are in the setting of transfer learning.
Yeah.
So we basically have a backbone, the unit, and then we want to have features from this, and then we're using these features to train our model.
Okay, what is it? What is our model doing? What is the purpose? What is the input?
So, for example, our input are images, and then we want to doing image segmentation. No, not image segmentation, image classification.
Okay, so why do you need a decoder?
Oh, sorry, I meant the encoder. Oh my God,
Okay,
yeah, I meant the encoder all the time. Yeah,
that makes much more sense. Yes, but the thing is, it's interesting. I'm actually struggling with this question right now because I'm trying to do something like this with my thesis. Should I use? But because I think that if you're using skip connections, you're not forcing the latent space to represent the best features from the image, because you mitigate the problem. You allow it to learn other stuff, and I'm not sure what will be there, but
Okay, yeah,
It
that's
is
exactly what I
very
meant.
interesting. It is very
That's-
interesting.
yeah.
I'm not sure. I'll tell you after I finish testing it. Let's see. Okay, so transfer learning. Okay, now comes the idea of freezing weights. And that's always a question, like, should I freeze, should I not freeze? So freezing weights is helpful when you don't want the current features that are extracted to be changed. When is that reasonable? Do we have it here? No. I think it's in the end we have it. Let's see. No. Generated model, this thing. Okay, so basically, for example, you trained, let's say, a classifier on autonomous driving dataset, and now you want to move it to classify dogs and cats. Yes, that means that you will need to train the entire things because the features that you're looking for are not the same thing. That they already extract, for example, edges and contrast and stuff that could be useful to fasten up or speed up the training process, but they're not relevant for your task. Therefore, you want to train everything. If there are similar ideas, for example, you have something to train on the ImageNet, and then you want to have to transfer it to Cypher. You could freeze them and not change them. I would just train them to fit better to the current task at hand. I would never actually freeze anything. Just the only reason to freeze something is that you don't need to do back propagation, right? And then it's much faster. And Rob, for your question from earlier, if labels are not given to you, or some things that guide you to solve a problem, then it's not a supervised learning scenario. So yeah, that's about that. Sorry for skipping from one thing to another. Let's see, where are we? Unless you have any other questions about transfer learning. I think that the thing that we touched most is what I just described. More than that, always use transfer learning if you can. Like, it's such a cool thing to do. Okay, let's talk about popular CNN architectures. It's not going to be a lot. Let's see, finally used for handwritten LNet. Okay, so the things that we need to know basically is the structure of most of them. Yes, and besides UNet, all of them has convolutions and then fully connected layers for classification because they are all used on MNet. Like very, this is, for example, MNIST, yeah, or something similar. AlexNet, we'd already discussed the important thing that the problem with it was the big strides and the convolutions, and VGGNet already removed it to 3.2. And usually it's like always default thing to do. It's not even for the exam, just default way to go about stuff immediately. I would say is to go 3.1.1 and then max pooling. It works amazingly well, and also extracts it extracts low-level features, and with the receptive field, as they go deeper, it manages to construct bigger and more meaningful features. To unfreeze the transfer pod, once the classifier that we have bolted. I would just not freeze them in the first place, because Or if, for example, if you are moving from one dataset to another, I would just let it train. Let them adjust to the new dataset. Well, I don't have a voice anymore, huh? About these, like usually, like sometimes they ask about VGGNet, what is the structure? Like there was one question that what is the structure? So they gave you some ideas, and you had to say, okay, it has convs, it has max pools, and it has fully connected layers. This, for example, it follows this thing. This is for example, for the exam. Yeah? A question in the exam. Okay, this one is important, and as we said again and again and again, is the important thing here is that we use these skip connections. They have to have the same size in order to be able to be summed upon, and we use it as highway of gradients, and it allows us to basically forget this stage if we don't need it, like with batch norm. Okay, it allows us to basically, so this is why we say skip connections will never make the network perform worse, because we can just simply forget these blocks. What else? Or you could just add nonlinearity. These just it's irrelevant, like to memorize. Like, why would someone memorize this? And fully, which one? 77512. Which network? VGG. You mean you mean these parts? No. Sorry. Looking at Alex. These parts, when you move from this to this, if it doesn't work, it's basically because they flattened it and they did it fully connected to move to there. Okay. If it doesn't fit, that's what happened. They flattened this one, so it's, and then move to 4. And had a fully connected layer there.
Sorry, quick question concerning flattening. I can basically flatten the 7 times 7 times 5, 12, however I want it, as long as it is consistent. So I can go through all the channels first, or I can go through every pixel in every channel first, as long as it's consistent throughout my training.
As long, exactly. As long as it's consistent, the network will learn to do what it gets with the relevant pixels. Especially when fully connected layers, right? Where they're all connected anyway, like they're all summed to the same place.
Okay, thanks.
No, you don't need to know the architectures and the dimensions. It's irrelevant. What is relevant is, for example, the AlexNet. What was the problem with AlexNet, right? And then we moved to 3/3. That is important. Okay, that's like a major breakthrough in how do we skip connections work doing backward. It's simply a back propagation through this and back propagation through this, which is basically like the derivative flows here. This derivative, the d out that goes to this layer just goes here also. So this one will have d out plus whatever comes from here. I think total amount of parameters was also in exam. Yeah, that's true. Very unfair. Not on my watch. You won't have this question. Okay. Like many exams, I have no idea what they had in their mind when they had this. But I will not ask you how many parameters in Alex. It's just meaningless. You could just Google it or ChatGPT. How many parameters are there? ResNet. Okay, anything here that I want to discuss? That's an interesting point, by the way. the deeper we go, it downgrades or degrades. Yeah, okay, there's just points about that. Okay, inception layer is something that is interesting. Okay, then what we see here. So why is it important what we did in inception layer? Because we introduced one-on-one convolutions. They introduced this different sizes of residuals. They did max pools with 3 and 3 and padding. Okay, there is padding here. Okay. What is the problem with GoogleNet? What could you think about it? Okay, we discussed a lot of stuff. Why is it not used in practice after all? It is like it has great ideas. You said, oh my God, what should we choose? Let's just take it all. Thank you. F expensive. You know, like because they're using so many parameters, so many, just Google can run this. So, oh. Many attentions. What do you mean? Okay, I'm continuing. I bet you're all exhausted as I am, but we still have a little bit more to go. We can have a small break if you want until 5. Yeah, okay, let's just do another 10 minutes, yes. Recording in progress. So if only some important questions that can maximum likelihood to come. So if only some important questions can. I cannot tell you anything about the exam. It's what's going to be inside, of course, right? But I am trying to guide you as good as I can to think that might appear. The way I think, and I contributed my share to the exam. So, you know, if you listened here, you'll be okay. That should not have been on the recording. Anyway, let's continue. What can I say? Okay, I have never mind. I have really black jokes right now. It's not the time. Yes, it is. Yeah, my brain is already jelly, you know, like you could see the way I function. Let's continue. Okay, recurrent neural networks. Let's continue. Come on, guys, serious. Why is it here? Maybe it wasn't in the same lecture back then. So recurrent networks, what we need to know. Okay, can you tell me an advantage of recurrent neural network? Do I need to explain how it works first? Does anyone need that, or we're all good at that? Team, is it yes for let's see how it works, or are you good? Please explain. Okay, thank you. Okay, so recurrent neural networks takes a sequence. For example, a sequence could be anything. It could be a sentence of embeddings, like for example, words that are transferred to embeddings first and then move to the network, or it could be a video, like frames from the video that has some relationship between them, because recurrent neural networks was first aiming to learn relationships between different inputs or over time. Okay, so first of all, we say TUM is, should I be careful here? A university. I wouldn't say that because then I would be lying to you. Anyway, so we take that. Oopsie. I just can't anymore. Although the informatics Sommerfest was anyway incredible, free Augustiner beer. What can you say? You know, it's never. Anyway, okay, so we take these ones and we push them into embeddings. Each embedding has to have the same shape. Okay, so we do whatever we need with this. There is many ways to do embeddings, and then we have these embeddings here. Okay, each cell has the same weight matrices. These weight matrices basically have X over, I think it's W, plus the H. This is H0, and then it moves on. So it's going to be HT and XT, or H minus T, T minus 1 to V. W and V are weight matrices that their entire purposes is to make XT and HT1 minus 1 as the same shape. And of course, process them a little bit. Okay, process them a little bit, and then we could add them on and have HT minus 1. Okay, which is moved here. And of course, it moves through some activation like ReLU or whatever. And we move again and again. Eventually, like there are many different kind of RNNs. For example, in this case that we see in this picture, we could output at each cell something. But in our exercise that I hate big time, exercise 11, our task was to classify if a sentence is mean or good, something like that, right? Overfitting alert, yes. Can RNN reproduce outputs of different sizes? No, like they all have to be at the same size. This is very, very simple architecture. So eventually, so we don't have these, we just had this, right? It was just an output, and then we did another linear layer to say, okay, are you good? Are you bad? Right. So this is just basically RNN. The problem with RNN is these W and V are shared across the entire process. Then they're used again and again and again. An advantage of it is that it's super, super lightweight. There are not many parameters here. There are this, and maybe a bias for each one of them. But the problem here that because we multiply with, so remember, yes, remember that affine layers convolute that the dx equals d out W transpose, right? So this is what moves here. And if the eigenvalues of this is lower than 1, then it means that we're multiplying this value again and again and again with numbers that are lower than 1, meaning they're going to diminish quite fast. Meaning, what is the vanishing gradient? Yes. Okay. What happens if the eigenvalues are bigger than 1? Exploding gradients. Perfect. Oh my God, this beer really helps. I gotta tell you, you gotta try it. Can't believe I'm gonna upload it later on. Okay, that's the biggest problem of RNN. Now, the thing that you could solve it with is make sure that the eigenvalues are 1. It's super hard to do. And definitely this is why it's not used in practice. Maybe the ideas are, but there are better ways to deal with this. So RNN, we said, okay, not good. It also lacks another things. What because of this? What does it lack? What other problems do we have? Long-term dependencies. Yes, very good. So basically, these because these are very far from each other, it cannot really discuss with each other, right? It has some idea of that coming through, propagates through the network, but it's quite vague. So we cannot really say that. On the contrary, like on the opposite, for example, with attention, with transformers, each one of them are talking to each one of them, so directly. And then we have direct attention or direct correspondences between them. That's one of the biggest things that transformers has solved. Can you fix this with batch norm between A? But batch norm is on the output on the neurons and not on the weight, and the weights propagates. Maybe with this initialization, but this the initialization has to be 0 of 1. It's quite hard. Remember what batch norm is applied on. Okay, RNN and skip connections. That could solve the problem, yes, but it's definitely after transformers were introduced. Bye-bye. Yes, there was a question about that in previous exam, in 2 of them actually. Last exam, like they wanted to do it also in previous semester, but I thought that they would remove it because it's such an unfair question. Like of course you need to know how to do it, but in such a stressful exam, I'd rather you not do it. You should solve the questions that you have there. It's good practice, you know, and if you see something like that, it's probably so we duplicate it. We will not change it. So if we see it again, you'll see it. It will be the exact same question. Definitely should not be recording. So we've been discussing that. Eigenvalues. And vanishing gradients and long-term connected. Yes, the vanishing gradient also. Yes, of course. But also that the fact that the gradient for V's and W's are becoming really, really small because they are multiplied by the D out that moves from one cell to another. But also because they just don't connect with each other. What solves this problem was this thingy of LSTM, which is the current state, right? Which is like a skip connection. Sorry. Okay, so the gradients could actually just go through it. And LSTM, the questions that we ask about it, so the questions that can be asked about LSTMs are, what problem of RNN that LSTM solve? Vanishing gradient, or exploding gradient, or the vanishing gradient, basically. Or the question, which one of the, like we give you the gates, put their names on it. No, but you need to remember that the gradients of V is also connected to it. That's true that the gradients so let's do it again, okay? HT minus 1 equals, let's say, activation over XW plus HT, that's Y minus 1, HT minus 1 V. Okay, so the gradients of, it depends what you want to do, of W will have to be according to W. Oh no, we want V actually, right? Not W here. We'll have to do something with this, and dependingly on this, and the D out that comes into it. So it will be a sum of many other things, but it will manage basically the fact that the lower, the more we go up the stream, the gradients will become smaller and smaller. That's what makes it, yeah, as you said, that the long-term dependencies are really hard. Can you repeat the last question? The gates. Okay, so there was exam questions about that. That we give you the names. You need to assign a name to the gate. But that's it. No more, like, because it's not used. LSTMs also are dropped ever since transformers came in. That just doesn't just, we teach it just because this is the basics. This is where it comes from. We should know where we come from, right? What was tried before, and then how it was improved upon. I think. Get concatenated. There are summed layer by layer, not concatenated. That's and what I mean, but what I meant with these layers, the shallower ones, their relevance is going to be quite small to the gradient. So overfitting to these, basically, to the deeper ones. Did I miss anything? So the thing is, do we talk about attention? Yes. Okay. Now, attention. Attention. Now, attention is something that in transformers are usually asked more in advanced deep learning, the course. Here they are taught, and the thing that we need to know, we don't have it here, do we? Fuck. Yeah, that's true. That it solves the vanishing because of the skip connection. Skip connections, it's also true for units. It doesn't solve the exploding. If you have huge values coming in, they will come in big time. So it just solves the problem of as we go up the stream. Remember do you remember like 8 hours ago when we discussed the difference between vanishing gradient and dead ReLU? That where the shallower layers will not train or will get the gradient with a much lower magnitude, and then will move much slower. We don't have attention here. It's a shame though. It's a shame. What if I do this? Can I click on it? No. Okay, it doesn't help. Next chapter. You have attention? Okay, anyway. I need to find for you, I need to put on to share my screen to talk about this. So let's just move to the things that are the last thing that are important for this discussion. No, different gates are in LSTMs. That's it. They have gates in LSTMs, and that's it. Transformers are a completely different thing, and it's again, most of the stuff of the advanced topics that we've discussed in this lecture, we didn't really discuss them. We didn't really teach them, so we don't really ask about. But some of them will have one question. Yeah, it just I know I can click, but it just doesn't work. Maybe because I'm sharing the screen or something. I know. Maybe I'll need to stop sharing and then I could go there and share again. Maybe. Let's see. Let me just stop sharing for a sec. Yeah. Stop share. Okay, and then illustrated attention. Why? Maybe because. Okay, perfect. Screen start now, and then. Do I need to sign in for this? How fun. Yes, Gao, you're right. Okay, never mind, guys. Let's just continue with what we have. That's not for you. That's for you. Can I just close this? Yes. So the thing that we usually ask about is variational autoencoder and GANs. GANs, very, very, very high details. Variational autoencoder are just a bit more, we go a bit more deeper, and that's something you do need to know. Although we didn't practice it, we didn't write it, like in one of the exercises. Can we, this response learning, so that's all we have about it? Really? Okay, so what we need to know about variational autoencoder. Okay, this is the latent. You know what? I could just do it here. Okay, let's say this is a variational autoencoder. Okay, what are the differences? We have a few. First of all, is how the latent space looks like. The latent space here has two latent spaces. It has this and it has this. Okay. The last layer creates both mean and variance, which the way we would, and then we can use a Gaussian to sample from, and with a reparameterization trick, we basically do, what was this? It's not important for your exam, like to know how to sample from the latent space. So I don't remember it by heart. But basically, this is what you need to know. So basically, the latent space is different than the latent space. It learns the distribution of the input by two things. We have two loss functions. We have reconstruction loss, which is the L2, L1, or any other variation of them. And we have the KL divergence. Again, that's the only thing you need to know. You don't need to know how to write the KL divergence. Okay, you just need to know that it exists, and what it does is constrain the distribution into these. Because when we sample them, the KL divergence takes only these two variables and takes the loss out of them, a loss from them. And this is what constrains the distribution of this inside them. Then, during testing or inference time, as we like to call it, we discard this encoder and we sample from a Gaussian distribution with 0 mean and variance 1. Okay, okay. So before that, so again, here in autoencoder, we just had the latent space where this was compressed into. In variational autoencoders, we have one for the mean, and we have one for the variance. Okay, if you want to, you could have the sigma. Katerina, yes, yes, exactly. And that's exactly what we do. Also with the reparameterization trick that I'm not touching right now, during inference, we sample some from a Gaussian, and then we let it be decoded through this. Okay, and the decoder knows how to take these kind of samples and reconstruct them into generate a new complete image. Sorry. Okay, that's the point of the differences between variational autoencoder and encoder. That's all you need to know. What's the difference in terms of loss between the two? So this autoencoder has reconstruction loss. I don't want to write reconstruction. So L2, L1, etc. Any reconstruction regression loss. On top of that, we add the KL divergence loss term, which takes the latent space and does something with it. I don't want to give you the formula. It's irrelevant. Okay, all you need to know is we use this on the both latent space vectors. Okay, to constrain the distribution of the input into this thing. And then we can sample from some kind of distribution, use the mean and the variance with the parameterization trick. It's just two latent spaces. One represents the mean, one represents the variance of the distribution. Not that I know, like I'm implementing it right now to my code, and it is such a simple line of code. Not sure it's just multiplication and addition. Yeah, that's already out of my scope. But we assume it to be Gaussian. Not sure why does it make it cheap or not, but I have no idea. Ah, yes, letters. Okay, what else? What else? So this is just autoencoder. Reinforcement learning we're not touching in this course. Maybe they said something, but so GAN. Okay, the only thing that we need to talk about a little bit about GAN and how it's reconstructed. Like there could be a question I think of cited one exam. That's true. KL divergence measures the similarity between two distributions. Just two numbers, right? What does that have to do with latent space or dump? Okay, I hope that answers your question. With GANs, what you need to know is how it's constructed. So basically, we have a latent space, and that's reconstructed into some image or whatever. That is sent into a discriminator. We take something from the training pool and we send it also to the discriminator. The discriminator is a simple classifier that only says it says for both of them. It takes them not together, but it takes each one of them and says, are you real? Are you fake? Okay, and it does this with binary cross entropy. This is the very basic GAN. Yes, that's exactly. And that's the thing is that this is we take the binary cross entropy and the loss so this is for the discriminator. as you could see here. Okay, and then the loss of the discriminator of the generator is going to be the opposite, because so they're fighting each other. This wants to know that it wants to find that these are fakes, and this wants to make such good fakes that the discriminator doesn't manage to. That's the very basic idea of GANs. The problem with it is this fight between two things could lead for a lot of things, for convergence to just the mean between the middle point between them, or to learn to do just to collapse to a single image that the discriminator just finds as true all the time, because then it will win, right? So there are many other things. I don't know why they teach you here this, because they don't dive deep into what it is. The input of GAN is nothing, basically. Like there are training set, so there are images that come from the side to the discriminator, real images that the discriminator is to say you are a real image. Okay, and this one is also an input to the discriminator, and it should say you are a wrong image. Besides that, during inference, this is not happening, this part, only generating from the latent space here and regenerating stuff. Team ask, what is a latent space? Latent space is this. It's this middle bottleneck that we have here, which we squeeze all the features through, and then we reproduce them or reconstruct them. I think that with that, I think we could finish this session for today. Let's hear some questions though.
I have a question.
Yes.
So gradient descent is computationally costly if we have 1 million samples of pictures, and then we use stochastic gradient descent, and let's say the mini batch size is something like 32 or 40 or 64, and then I still didn't understand what we are doing and how we calculate the loss. So I put every image one by one to the network, and then train the network with it, and then calculate a loss, right? And then after the whole mini batch, I do the back propagation for the weights. And for the next mini batch, I use these new weights for the next 46. Is that true, or am I missing?
This is stochastic gradient descent. Yes.
Thank you, because I just always confused, and yeah.
So gradient descent takes the only difference that it's during the epoch at the end of the iteration, it accumulates these gradients but does not do the optimizer step.
What do you mean? Can you please clarify a little bit more?
So it accumulates the gradients, like it does gradients say take a batch of images, calculates forward, does backward, has a gradient, puts it in some tensor. Then it does another one, forward, backward, accumulates it into the tensor to the same tensor. It just adds again and again and again and again. At the end of the epoch, it will divide by the number of iterations. So we will have the average for each one of the weights in the center, and then we'll do the optimization step using any of the optimizers, which is Adam, SGD, RMS prop, whatever. And then it will do one optimization step towards the minimum with the given gradients, that the accumulated gradients that it calculated.
So one epoch after the optimization. So it means, let's say 1 million images, 64 mini batch. If we divide it, we get something like 16,000. And then for whole 16,000, I have only one update, right?
Yes.
Okay.
Yes.
Okay.
That's why it's never used in practice.
Okay.
Let's see, what else do we have? What we should know about reinforcement learning for the exam? Nothing. We're not going to ask you about reinforcement learning. You said you would work through some exam questions. I assume you refer to questions from already published previous exams, correct? To make sure that no question of my simulation exams are used. Thank you very much for the recapitulation. I could, if someone, it's only if you bring some questions. I'm not going to look for now for exam questions. SGD with batch size 1. No, but again, the difference between GD and SGD is when we do the optimization step. GD can be with batch size, with any batch size that you want. What kinds of questions that were asked in previous exam will not be asking the same around? You mentioned that we should be not just should not be any just googly things like never found such. Yes, like listen, a lot of previous exams, just I don't understand why they decided to ask that, like how many parameters are there, because they just didn't have anything, that they just really didn't care when they wrote the exam. 60, like how many parameters are in AlexNet? I don't care, really. Like but a lot of other stuff could be like, I cannot really tell you now what yes, what no would be. I can tell for reinforcement learning or graph neural network, definitely not going to be in the exam. Like, there's no reason I will ask you about that. And for SVT2,
I just